Welcome to the WebAssembly course 2024. So WebAssembly was talk of the town of 2023 and it is getting even bigger and bigger with all the fancy stuffs getting added to it in 2024. And I, Saiyam Pathak, joined by
Rishit Dagli.
thought that this would be the perfect time to bring a WebAssembly course for you, where we'll be talking about history of WebAssembly, what is WebAssembly, all the stuffs with respect to cloud native WebAssembly, how it works with Docker, how you can use the same tooling, how you can deploy applications, create them, OCI artifacts, deploy to Kubernetes, and all these stuff.
Yeah, particularly we talk about Wasm in terms of cloud native. We'll also take a look at a few applications of it. Mainly, we'll be focused on understanding the fundamentals of WebAssembly very well. The course won't be just showing what you can do with WebAssembly. Well, we'll also have some of that, both of us being excited about WebAssembly and what it can do. But the course will mainly be about answering the why question. Why does WebAssembly even exist? Or what kind of problems is WebAssembly trying to solve? And how is it doing that? What is the approach to doing that? You can think of it as we'll walk you through every decision with WebAssembly and understand why WebAssembly is made the way it is made and what kind of problems it's trying to solve.
So we are very excited for this particular course as we'll be covering everything from the introduction basics, the terminology, sandboxing, the runtimes, component model stuff, the WASI stuff. Everything will be followed by a demo so that it's not only a theoretical introduction, but it also practical introduction. We'll try to cover all the aspects of it. Yes, this is the WebAssembly introduction course for 2024 that you'll need to get your hands dirty with WebAssembly and create some fancy practical applications after watching the course. So we are very excited for this particular course. I hope you are too to watch till the end. WebAssembly. Is it web? Is it assembly? What exactly WebAssembly is? In this section of the course, we'll be discussing all about WebAssembly, getting the introduction and the context right, so that we exactly understand why this technology exists, why the terminology of WebAssembly exists, why it was needed in the first place. And then from there on, we'll build up to the cloud native WebAssembly, where we'll be deploying a simple application and a high level application onto Kubernetes environment. And that will be a WebAssembly application that we'll be deploying onto Kubernetes. So WebAssembly, is it a replacement for JavaScript? Does it replace Docker? Because we have been hearing so much about Docker versus WebAssembly. Is it a new Java? Because Java promised some of the features that we'll be discussing about WebAssembly as well. Is it a new programming language itself that we have to learn a new dimension altogether to write software? What exactly WebAssembly is? Let's go down the memory lane and try to understand from the first definitions and the origins for WebAssembly. So as you can see, WebAssembly defines a portable, size, and load time efficient format and execution model specifically designed to serve as a compilation target for web. And that's exactly what WebAssembly is. Now, this definition is obviously used a lot because it exactly depicts what WebAssembly is. It is a compilation target. So there is a universal bytecode that your program or the code compiles to that can run on any platform. And that's what exactly defines the WebAssembly. It's not that this whole is a concept which is super new, which is like an innovation that has never been attempted before, and it's not like this has not been even discussed before. So there were promises that were made prior to WebAssembly coming into the game, doing the same thing, following the same approaches. There were attempts to do similar kind of things like running in the browsers, the fancy codes, apart from the JavaScript. But those were very language specific things. Like it was not language agnostic. So few of the examples that you might have heard is Java applets, VB script, Adobe Flash. You might have used a lot in the past. Now those were some of the similar attempts that I would say has been done in a similar area. So if you want to compare what WebAssembly is today. Today, it's a massive ecosystem. There's actually a landscape in CNCF also about WebAssembly. But yeah, some parts, bits and pieces you would have seen in Java applets, VB Script, Adobe Flash that you might have used in the past as well. Now, why WebAssembly was a success? Like, it's not only one thing. So there are few things. First, it's the joint effort to make a success. What does that mean? Is big companies coming in together, thinking, formulating a solution to have something universal, and putting effort in doing that. Things get interesting when it gets adopted as the fourth language of the web, because as per W3C, prior to WebAssembly, it was only HTML, CSS, and JavaScript. With WebAssembly getting into W3C and W3C making all like the standards, so the belief that this technology will succeed obviously increases because it is a standard being made by W3C. Now that's very interesting because it puts a lot of weightage that this technology will go a long way and the vision goes a long way. Instead of language focus that you can see on the Java applets, VBScript, and Adobe Flash side, so instead of language focus, the focus was on this new binary format. And obviously the security, sandboxing, things that we'll come to later. But that was the goal, language agnostic, platform agnostic, rather than making it language specific stuff. So that's what in a nutshell is WebAssembly. Very quickly, like one sentence, it's just a compilation target, a universal bytecode that is platform agnostic. So your code will be there. And when you compile that to .wasm, which is a Wasm module or a Wasm component, and you will be able to run it on any platform where you have the WebAssembly runtime. So that's what WebAssembly is. So let's try to understand even before WebAssembly and Java first. So when anyone writes the code that machine understands is the machine code. So user will be writing the code. It gets executed as machine code because the CPU understands only the machine code. So the machine codes get executed by the CPU. These are basically the binary numbers, the format that is a CPU instructions, which comes as ops code, which tell what does a CPU need to do. Now, people, obviously, when things were getting started from machine code, it went to the level where assembly came in, so that assembly can make things easier for it to write, so that you don't have to write the machine code by hand. And assembly made these instructions more readable. Now, due to different set of architectures, different set of CPU architectures, it was becoming, again, difficult to write the machine codes, the assembly programs specific to each and every architecture. It was a repetitive task for the developers, for the vendors. So that's where came in the virtual machine code, and that helped in reducing further, like abstracting it further away from rewriting and developers only focusing on writing their code once. Virtual machine code, virtual CPU code is actually the JVM bytecode that came in. So that is what JVM is, very specific to Java languages, and that is where when we compare WebAssembly or aka Wasm, I will be using those interchangeably. So WebAssembly is language agnostic. JVM was language specific because it was only focused around Java. So next up is the strict sandboxing. Now, before we actually move to this point, we need to understand what sandboxing exactly means. So sandbox in general, as the name suggests, is a controlled environment where your code executes without affecting the rest of the system. For example, you have a house and you have a baby in one of the rooms. She's playing, and in the other room, it is not affected where the meeting is going on. So very small example, because it happens to me where my kid is playing in the other room and I am not affected in this particular room. So her activities are sandboxed to that particular room. So that's why I just gave this example. Now, WebAssembly is obviously, that I said, is a universal bytecode format. When WebAssembly runtime is running the code, so the runtime is making sure to make that WebAssembly code run in an isolated environment, which is separate from the host runtime. So it makes sure that your module execution and your host runtime are separate. Next thing, how exactly this happens is basically Wasm provides a secure environment to run your code inside the browser, because that is what it was originally built for the browsers. Now, Wasm directly doesn't touch your systems. It only use the specific web APIs to do so. Like the runtimes only use the specific web APIs. And it has a separate memory buffer, keeping it away from the other apps. That's how it is like a kind of an isolated memory, have its own isolated memory. And there are specific checks that that the browser checks for the Wasm code. It avoids the security pitfalls. Policies ensures that Wasm modules respect the website boundaries, and modern browsers also have the built-in protections to further shield against it. The simple point here to make is that this is a sandbox. You cannot access anything outside of the browser, or even if when you are running WebAssembly on the server side, you need specific philosophies like WASI, WebAssembly System Interface. If you actually want to access any particular resource explicitly, you have to mention that. So there are very specific ways if you want to do stuff, but all in all, it is a complete sandbox. Also, if you have a shared resource pool and you have multiple WebAssembly modules that are consuming it, it is very hard to maintain that security level. So Wasm, which is on the philosophical side, and the runtime implementation that actually makes everything possible, whatever is written in the specification of WebAssembly. So the runtimes makes it provably possible and makes the secure sandboxing as the strict sandboxing. So that's where your code is actually running. And that's where when we talk about running the sensitive code or giving it on the browsers where people can put malicious code, won't affect your overall systems, because that runs in a specific sandbox, doesn't have any resource request with respect to your host. So it will be running isolated and securely. So that's what strict sandboxing is. And this is where WebAssembly has the strict sandboxing and JVM doesn't have that strict sandboxing. W3C standard, yes, as explained in one of my previous videos, that Wasm was accepted as a W3C standard, which made it more adoptable solution for the long term for language agnostic universal bytecode. Coming to the timeline, timelines are important because it's important to know some of the events with respect to the years. And that's where I want to share that it is not a very new concept, thought, or philosophy. People have been thinking to do it from a decade, like over a decade. But yes, as things have matured, the use cases have matured, the adoption have matured, the production implementations using WebAssembly has matured, and with successful use cases, successful company adoption, things have accelerated a lot. That is why we hear a lot about WebAssembly in 2023 era. And that is why we are creating this course, so that we understand exactly what WebAssembly is and how to use it effectively. So in 2012, the ASM.js came into picture. And then there were some of the enhancements going on in that specific field, people coming in together, brainstorming together how to form a universal bytecode. After that, in 2015, you got the WebAssembly initial announcement, and that's where things started to take a nice turn in the history of WebAssembly ecosystem. And in 2017, it made more and more progress for the WebAssembly on the browser side. And 2018 was when the first public working draft was made and the threads support was introduced. In 2019, now this is very critical year, because now the browser adoption was getting a lot. People were adopting use cases and many applications, online gaming, all these things were happening on the browser side of things. Then things turned onto the server side, and this is where the web standard and standardizing of the WebAssembly system interface happened in 2019. And that's where we'll talk about later as well, when the first post for the WASI was introduced. That actually created a lot of buzz in the cloud native ecosystem, and what exactly triggered it, we'll go through that moment as well. Moving forward to 2020 expansion, obviously on the Wasm ecosystem, more tools, more languages, more frameworks to ease out the tooling, more language support, meaning the language itself, the compilers itself, the generic tooling like Cargo and all itself starting to provide the support natively for WebAssembly so that you can just easily compile and target your compilation code to the WebAssembly format. 2021 came in the first draft for the component model. Another very interesting thing that people are excited about a lot, and we will dive into component model in upcoming sections. 2022 WebAssembly core specification V2, because as the technology matures, the number of the demand becomes more, like we want to do this, we want to do that, we want to do more and more and more. And this is where the WebAssembly core specification version V2 has been going on. 2023 has been interesting. This year saw major conferences, I would say. One was the Wasm IO and one was the Wasm Con, the first ever very big full-fledged Wasm conferences. So that shows the education for WebAssembly and need for people to come and speak on different use cases, patterns, how to do, how they are using, and very interesting things on WebAssembly coming in all together. And that is where the enhanced component model are on the final stages of being published. Another very interesting turn 2023 is seeing at the time of the recording is the Wasm ML inferencing. So machine learning inferencing as WebAssembly modules is becoming more and more trendy and popular, and it solves some of the cool use cases when we talk about machine learning inferences. So that's a gist about timeline for WebAssembly, starting from the ideology and some of the thinking in the same lines that WebAssembly is today, starting from 2012 to 2023. And I think the future definitely looks bright. And we'll talk more as we progress in this course about the server-side WebAssembly, cloud-native WebAssembly, WebAssembly, Docker, WebAssembly, and Kubernetes. Coming on to the WebAssembly success in the browser. So basically, the overall agenda was to run the code that they are having into the browser. See, the thing is, in that era, why everyone was thinking that? Because the browsers were becoming more and more popular of the consumption of the application. So it was not only the desktop applications that the organizations wanted to give to the users. Now, this is very important because this also kind of relates to why people started to think about WebAssembly in the first place, why they want to run their application, their desktop applications, which are running successfully onto the browsers. This is because the browser adoption was increasing rapidly, and the organizations wanted more and more of their products to be consumed, and the best way that people were consuming content at that particular point of time, and it has grown exponentially since then, are the web browsers. And that's where company wanted to port their most used applications onto the browsers. And it was difficult because those were not JavaScript applications. They were written in traditional languages, C, C++, having the maximum performance level. So Adobe and major companies have used Emscripten, which is a tool chain that converts the LLVM IR to WebAssembly. And this is where Emscripten has been instrumental in demonstrating the potential of WebAssembly and helping the transition of full applications, part of application, or the modules to run inside the web browsers. So after that, you have Figma. Figma also started with ASM.js and they ported to WebAssembly, and Figma is also widely used application. So I think when I talk about success in the browsers, these two comes to my mind instantly because of the level of usage that it gets, because the Figma templates that are being built, the Adobe Photoshop editing that people do, and these are very heavy applications when you run on as desktop applications. So you need that smoothness, and that smoothness meaning when you are drawing something or when you are putting this thing over this thing. So that smoothness means the near native speeds. So that speed has to be there, and that's what WebAssembly helps you give. So it gives you the near native speed. So we have talked about the strict sandboxing. It gives you near native speeds, and that's where I think the most powerful combinations comes in. And obviously, WebAssembly also helps you to run your code in the browsers, run your other code which is not in JavaScript or these languages. So you can use your C, C++ or any other language that can compile to WebAssembly to be run into the browsers. So you can write in your choice of language and you should be able to run that, and you get that performance tuning set in your head and in your language, and then you are able to run it. These are such true powers because you see the smoothness is pretty critical, and you feel when you are on these websites doing it. Google Earth also uses WebAssembly. Google Earth is basically a static, kind of a 3D game, because you can revolve around the globe, you can see what is happening, and it is so smooth. And WebAssembly makes it so smooth because there are the WebAssembly functions modules that are running over there. And there are a lot of other use cases like the online gaming, the multiplayer online gaming, which is there. So you are doing that multiplayer online gaming and you are making sure that it is being so smooth. Like you are firing here and you are able to see that. So I think that is the success that I call for the WebAssembly. So that is the success in the browser. So WebAssembly is write once, run anywhere. Though, in my opinion, the true power, because actually the tools these days are very mature. So even if you want to compile for different architectures, it's not that difficult. You can use the standard tooling to compile to different architectures. Though it is one of the features of WebAssembly, that is a universal bytecode. But the true powers that, in my opinion, are the secure sandboxing, near native speed, write in your own language and then compile to WebAssembly and run it and ship it, and the smaller binary sizes, because it's not like Docker where you are, having your dependencies, libraries, everything packed up inside as a container image. That's where like people compare it, the WebAssembly and the Docker ecosystem. But yeah, it's the code that you have to run. Think of it as a serverless model for a second, and then smaller binaries that you can execute. So the secure sandboxing, near native speeds, polyglot, and smaller binaries are the true benefits when it comes to the WebAssembly ecosystem. Now, I have heard it before because you might have heard similar sort of things when JVM or Java came into the picture. But the thing is, again, it is language specific. Now, this is language agnostic, and this is a W3C standards that again makes itself, way ahead in the leap. And that's where you can see the adoption and the success on the browser. If you look closely, you can see that there's a C, C++, or Rust or Go code which you compile to the WebAssembly module, and that runs with your HTML, CSS, and JavaScript as part of your web application. On a very high level, it looks like this is how it is. Like you have WebAssembly module and it runs alongside of your HTML, CSS, and JavaScript code. But wait a minute. The isolation and security, multi-platform, smaller binary size, instantaneous startup times, doesn't that ring the bell? Do you only need it for the browsers? And that's where the whole conversation was driving. Like these are the benefits that everyone needs. It's not the benefits that only the browser needs. So that is where WebAssembly was started for porting applications onto the web with the goal that I told you. But soon people realized that this has a huge, huge potential when it will go to the server side. And that's where things started to get interesting for having a new, you can say, concept within the WebAssembly ecosystem for running WebAssembly on the server side. So those are the evolution waves. Matt, who is the founder of Fermion, he termed WebAssembly as the next in the evolution waves. Not only him, but there are many, but I personally have heard from him. So you had servers in the past, and then you abstracted those servers with the virtual machines. So you click a button, you get an instance in the cloud. And then you have the next evolution wave, which is container. Wow, I can abstract even the virtual machines. Actually, it's the abstraction of the operating system, but still, you have the abstraction level over there where you can run multiple containers, and you can just package your application and run any containers on the same virtual machine. The next evolution wave is even smaller, which is WebAssembly. So it is even smaller size, and it's just the code that has to be executed, which does not have any relation to the host operating system that is running on, environment that it is running on. And if you have to give any access, it has to be given explicitly. So it's basically deny by default, and you have to give explicit access via the specific tool chain like WASI, which we'll be talking about later on. But yeah, that's where on the evolution cycle WebAssembly sits, and especially for the serverless application edge use cases, for the edge appliances where you have very less memory, you can easily have WebAssembly runtime and run your WebAssembly modules on those devices. And best, as the startup times are instantaneous, it powers the next generation serverless. That is why many of the startups in the WebAssembly ecosystem are providing the next gen serverless space or the next gen serverless service based on WebAssembly, because it actually makes sense. Because of the cold startup time, there's no concept. It just starts instantaneously. So those are the evolution waves when we talk about the server virtual machines, containers, and WebAssembly coming next. Let's try to understand it from another angle. So there is a user writes code. So a user writes a code in Rust, and that's a simple hello world program. And a user is able to use same tool chain, which is commonly used Cargo, to build and just target it as Wasm32 WASI to build a hello.wasm executable file. So the hello.wasm is actually platform agnostic, able to run on any architecture where you have the WebAssembly runtime. This is how the instruction set looks like, and this is the VAT for that. So you have the WebAssembly WAT format like this, and this is the JavaScript code to execute that WebAssembly module. So that's a pretty simple stuff. That's how it looks like. So you have a WAT, you have JavaScript equivalent code, and then this is how the instruction set looks like. And when you compile it using the same tooling, you should be able to run that on any architecture using the WebAssembly run. So we just talked about WebAssembly on the server side, that due to the benefits of WebAssembly, which is the faster startup times, secure sandboxing, instantaneous startup times, smaller binary size. So these set of features are pretty important when we talk about servers as well. But things are not as simple as it sounds when we talk about server-side WebAssembly. Let's try to understand some of the use cases, like why actually we would be needing server-side WebAssembly. So WebAssembly on the server side has been ever-growing area of interest since the start of the success of WebAssembly in the browsers, and it is mainly targeting the high performance computations, like wherever the high performance computing is required. More and more machine learning inferencing use cases we can see, image processing, video processing use cases, for simulations, for running untrusted code, so for running the secure sandboxing. So wherever you want to run the secure code, the sandboxing part of WebAssembly can help. That's where on the server side it's great to have that. Game servers where you can have multiplayer type of games, that's one of the big use cases. On the edge, on the IoT devices, there it becomes really interesting. WebAssembly enables the code to run with near native speeds, taking the advantage of common hardware capabilities, and again, it's platform agnostic, portable. That's where the power lies. Some of the interesting use cases which are already there, widely used, you can see on the server side as well. You have Cloudflare workers, allows running the WebAssembly at edge, bringing the competition closer to the user. Then you have Fastly. Fastly Compute at edge utilizes the WebAssembly for the serverless functions. Then you have Fermion. They use WebAssembly to power the serverless. So actually, WebAssembly is powering the next gen serverless. Shopify, storefront, backend, dashboard. Shopify also leverages WebAssembly for image manipulation, data processing, for enhancing their efficiencies. So I think these are some of the actual use cases used in production, used by many folks. But others, as explained, like for high performance computing, machine learning, distributed computing, like all the multiplayer games, Unity, there also a lot of WebAssembly makes sense. So those were some of the use cases. But again, as mentioned, when we talk about WebAssembly on the server side, it's not as straightforward. You need something to be done, and that's what was being developed. So if you see, when we talk about Wasm on the server side or WebAssembly on the server side, the most important stuff that you need is you need to do some interactions with the host. You need to maybe interact with the files, read a file, write to a file, directories, environment variables. I mean, those are some of the basic stuff that you would need for any application to make sense when you want to run on the server side. But WebAssembly being WebAssembly, it does not know about the host. So how can we do it? Keeping the secure sandboxing in place. So that's where WASI proposal came in, and in 2019, WebAssembly system interface proposal was there. Its implementations are done by the WebAssembly runtime. So when you install WebAssembly runtime, you can use a WebAssembly system interface for your applications to interact with the host operating systems to do some of the tasks which are required, like accessing the environment variables, files, and directories, keeping the sandboxing in place, because you only give very specific access via the WASI to access in a secure way. So that's what this is all about. So looking from another angle, again, WebAssembly system interface, two major things that were always in mind, even when the whole people behind the WebAssembly talked about the WebAssembly on the server side, was security and portability, basically for making WebAssembly usable outside of the browser. So any application call that you see when you do with the application, it actually goes via the kernel, via the syscalls. So those are called the syscalls. It goes via the kernel and then it accesses the file system and stuff like that. This in WebAssembly, if it has to be done, it is being done using Wasm. And Wasm module does not compile to a specific OS, so it needs something, and that's what WASI is. So I hope you got a gist of WASI. There will be another section where we deep dive into WASI, how it actually works behind the scenes, and some of the more deep dive concepts of WASI. But on a high level, for making WebAssembly to run on the servers, this thing made it possible, and this opened up the n number of use cases. Another very interesting thing that I am very excited about, and most of the WebAssembly community as well, is the component model. So I'll give you just a brief over here, and then we have a separate section where we deep dive into the component model, including the demo. So think of a code. WebAssembly lets you write code in any language. So think of like you are writing a code in Rust or in Python, and you have written something that can benefit a lot of other users as well. So you package that, and the other person is able to just import what you have written and use it in their program. So that removes the duplicacy that you might have to write. It improves the reusability. So you will be able to use anybody else's component that does a specific functionality in your code. So you will be able to import the code written in any other language, which is WebAssembly module basically. So you will be importing that WebAssembly component that has a specific set of functionality. Use that in your code, in your application, in your business logic, and then create your application. So it improves reusability, language neutral plugins, and it is being driven by the same under W3C with specific standards, security and portability, and all those security features in. So I think component model is what people are really excited about. It's on the verge of getting published, and we'll dive more into component model in the future section, where we'll be going through a complete end-to-end demo as well to see this in action. So now we know that there is a lot of buzz, excitement, and actual practical use cases when we talk about WebAssembly, whether it's on the browser side or it's on the server side. Now things are evolving rapidly and really, really fast. There are a lot of adopters, like very big companies, BBC, Adobe, and all these companies which are there that uses WebAssembly. And then there are a lot of fancy startups, very good, like Wasmer, Dialypso, Cosmonic, Fermion, Second State, and many others that are doing very great research work and taking WebAssembly to the newer heights, and also participating in the standardization of the different projects within the WebAssembly ecosystem. So I think the companies are evolving continuously. The interest from the established organizations are evolving continuously, and there will be more and more and more of these things. Now, as the CNCF landscape has evolved over the years, like I have been the ambassador for like so many years now, I have seen the landscape evolve. I have seen the Kubernetes whole ecosystem around Kubernetes evolved. We are seeing kind of the similar things with WebAssembly, where people are kind of, using it at the early stages, thinking of it like the early versions when we had Docker in place, and some people were experimenting, some people were doing R&D research, and some early adopter of Kubernetes, and then slowly it becomes the de facto standard. So it's in those kind of stages, and there is a lot of innovation, a lot of work, a lot of research, a lot of great startups coming into this area. But since all these things are a lot, there needed to be a certain place for this, and what better than a CNCF landscape? So we already know that CNCF landscape is massive, and we enjoy navigating through the CNCF landscape. I have given a couple of talks on how to navigate a CNCF landscape a proper way. But now if you go to landscape.cncf.io/wasm, you will be able to see everything with respect to WebAssembly. So you can see you can see a lot of things like different set of languages. You have Wasm specific one, Grain, and all the other languages which are there. And then you have the runtimes, which are the core essence part of the WebAssembly ecosystem. You have Wasiro, you have Wasm Edge, you have Wasm Cloud, you have Wasmer, and so on and so forth. Then you have the application frameworks for building and making easier to build the WebAssembly ecosystem, like Xtism, Spin are the very popular ones. And then you have the edge and the bare metal AI and machine learning section, observability options like mod server, observe SDK. We have decentralized platforms and hosted platforms that provides WebAssembly services, the serverless offerings, Fermion, Flows Network, Fastly, the Cloudflare workers. You have the orchestration and management, and you can see the KWA, which is KWasm that we just discussed, Run WASI that we just discussed, Yolki, which is also there now in the shame. Again, just like the CNCF landscape, it gives you a great way to track what is happening within the WebAssembly ecosystem. So I think that's a great way so that you can get your heads right. Okay, this is the stuff happening in the WebAssembly ecosystem, and you are able to think and analyze some of the projects. What are open source projects in this area? What are some of the organizations providing the hosted platforms in this area, so that you know what people are using in different ways for WebAssembly on the server side and with respect to cloud native. I think there's a lot of integration. There have been a lot of cool projects when we talk in the CNCF ecosystem as well that uses WebAssembly. A lot of organizations who are CNCF members that uses WebAssembly. And when it comes to Kubernetes, Docker ecosystem, it definitely fits into the CNCF ecosystem. So yeah, wanted to give you a gist about the cloud native interactive landscape for WebAssembly. Let's talk a bit about Bytecode Alliance. So Bytecode Alliance is a non-profit organization dedicated to creating secure new foundations, building on standards such as WebAssembly and WebAssembly system interface. Bytecode Alliance is establishing a capable, secure platform that allows developers, service providers to confidently run untrusted code on infrastructure for operating system devices and stuff. So basically, it's the foundation for WebAssembly ecosystem. You can see the great members in this particular ecosystem who are working towards the standardizations of the WebAssembly projects. So you can see some of the projects that are there in the Bytecode Alliance, like the Wasm Time, Crane Lift, Warmer, Javi. It basically maintains the security and the sandboxing for the WebAssembly projects, and the standardization is going in the right place, right direction. The effort of WebAssembly is solving the cross-platform stuff. So there is cross-company collaborations that have to take place, and there has to be a foundation. There needs to be a foundation that takes care of all the meetings or the working groups and all those things. I think Bytecode Alliance has now have a TOC. There are different members on the TOC from different organizations who are working in the WebAssembly ecosystem on different runtimes, and they are collaborating on all the W3C standards with respect to WebAssembly, on the component model, on the WASI ecosystem, on the AI inferencing standardizations, and they are trying it under the same foundation so that everyone agrees, and we are following the right approach for doing this, following the basic principle of security and portability when it comes to WebAssembly. So that's what Bytecode Alliance is. In my opinion, like Bytecode Alliance is for WebAssembly what CNCF is kind of for Kubernetes. I kind of see it in this way. So you can check out all the news about and home and membership and all that stuff around GitHub, how it is happening in some of the meetings of the Bytecode Alliance as well.
So let's talk a bit about Wasm Sandbox now. And Wasm Sandbox is one of the important parts of keeping the WebAssembly promise of secure runtimes. Taking from the WebAssembly design, the security model of WebAssembly has two important goals: protect users from buggy or malicious code, and provide developers with useful primitives and mitigations for developing safe applications. And this is particularly useful because WebAssembly was originally designed, and most of how it is used right now is running WebAssembly functions. And what this means is you have some function or some part of your code written in some language you compile it as a WebAssembly module and use it in some other languages. And this particularly requires you to run untrusted code. So this particularly makes sense considering how WebAssembly is mainly used. One popular approach that might come to one's mind is SFI, or software fault isolation techniques. But before talking about SFI, let's talk a bit about sandboxing. So what we want with sandboxing is just have some security mechanism that isolates a program or process from rest of the system and allows it to run without compromising the security of other parts of the system. So let's say if you want to incorporate third-party libraries into your code or just run Wasm modules in some other program, you may need to run untrusted code, which poses a big risk to security of the host environment, since malicious code could potentially compromise it. So this is why you need sandboxing in the first place. And for a lot of these applications, having a full-fledged VM becomes really heavy, and you most certainly have other benefits of WebAssembly. But in terms of sandboxing, having a full-fledged VM becomes really heavy to do this. And one of the first things that comes to one's mind when trying to do this sandboxing or have this very thin sandboxing layer is SFI, or software fault isolation. So if you didn't know about SFI, this is mainly based on the key insight that you could encapsulate potentially faulty code in isolated compartments. And it comes with the key insight that it is possible to limit the impact of any errors or bugs within those compartments, and you can protect rest of the system from harm. Now, you can also formally verify that these isolation mechanisms themselves are correct and functioning as intended. The way you would do this is you want to verify the compartment boundaries are properly enforced and that data passing between compartments is correctly validated, and that any errors or exceptions raised within a compartment are properly handled and do not escape to other parts of the system. So, despite the promise of SFI and formal verification, their adoption has been very limited due to multiple deployment challenges with SFI. So let's take a look at how Wasm, or more accurately, Wasm runtimes do this. So first, what we need to understand is that this needs to be implemented by the runtime itself. And this does mean that we could create a Wasm runtime that runs this non-native instruction set WebAssembly very differently or gives it complete access to the host. Or you could also have a Wasm runtime. There are actually quite a few Wasm runtimes that use SFI techniques to do this sandboxing. So you could also do that. So it all depends on a Wasm runtime. But usually how a Wasm runtime does is you separate the core Wasm language from the specific API provided to each Wasm module by the runtime or other modules. Thus, Wasm enables the creation of like these diverse runtimes that cater to various needs. The way you would need to implement the sandboxing for Wasm modules would also be in the runtime itself. So this also means that any external third-party libraries you need would need to be linked with this Wasm code. Earlier, we used to have a tool called Wasm Linker, which is now a part of some other popular tools you'll take a look at later in the course. That is the way you'd often want to use any third-party libraries and separate the core Wasm language from these specific APIs. This is exactly why a lot of things become challenging as well. This is exactly why there's a need for something called WebAssembly system interface, which we'll talk about later in the course. But doing the sandboxing this way does cause a lot of challenges. So we'll also talk about how to get around the challenges and what those challenges are later in the course. A big part of this is also due to how memory is represented in WebAssembly. Memory in WebAssembly is represented as a contiguous, mutable array of uninterpreted bytes, which dynamically grows in size. Usually, Wasm runtimes have 64 kilobytes of page size, and the bytes can be mutated by the WebAssembly module through memory instructions. And there's particularly also parts of the WebAssembly memory or the parts of WebAssembly linear memory that can be exported. So when the WebAssembly module sees that you want to export particular parts of the memory, you can also have the host machine access that memory and modify that memory as well. Originally, WebAssembly linear memory in early days of WebAssembly, when WebAssembly was only supposed to be run on the browser and there was only tooling to do that kind of stuff, run WebAssembly on the browser, you would have your WebAssembly linear memory as a JavaScript object. You can think of it as all of the linear memory that you need for a particular module would be a simple JavaScript object. Now, most certainly, you don't need it to be a JavaScript object because there is enough tooling around WebAssembly to run it in diverse contexts and not just on the browser. Another thing to note with this linear memory, which particularly ties in well to the security aspects, is that the indexes of the linear memory can be considered as memory addresses. And the instructions that you need to access a memory location are given an offset relative to the start of the memory. So there's no direct addressing possible. You can only have an offset that is relative to the start of the memory that you can access. We can also take a look at a code example to do this. But what this allows you to do is you can have modules with potentially harmful code, and it is very easy for the runtime to understand if they are trying to assign linear memory outside of their memory space. Even if one WebAssembly module is trying to access the linear memory of another WebAssembly module, it's really easy for the runtimes to identify this. And the runtimes also know exactly how much memory it is being used. And thus, it is also easier to identify if a module in WebAssembly is trying to intrude into memory spaces of other modules. So let's take a look at this very simple example with Wasm Bindgen. We'll not try this example out for ourselves, but you can very easily try it. First, what we do is declare that we want a WebAssembly linear memory of size 2. So that's what we define first. And then we have multiple functions that set some value in the WebAssembly linear memory and also read some value from the WebAssembly linear memory. And you can also do this low-level tasks very easily with Wasm Bindgen. So you can very easily do this with the linear memory. Although you most likely, for a lot of your applications, might not need to do these particular things with Wasm Bindgen. So linear memory solves a lot of problems. Particularly the problems that this kind of linear memory solves is dereferencing pointers to unallocated memory, which, if you remember, is a big problem with C. You had tools like Valgrind to identify memory leaks. And if you had malloc some object and you delete the reference to that allocated memory, it used to be a big problem. And linear memory solves all of these problems. It also solves freed memory allocations. So linear memory does solve all of these problems, but in WebAssembly, the semantics for a pointer are also a bit different. Especially with WebAssembly, you don't have a semantics for a pointer, but you have function calls and variables with fixed static scope. So any references to invalid indexes in the index space trigger a validation error at the load time itself. Even though WebAssembly solves all of these problems with the linear memory, there are a few kind of attacks that the WebAssembly linear memory doesn't solve. For this, we especially take a look at how Wasm gets around control flow integrity issues. And we'll take a look at how WebAssembly Sandbox helps you to solve these. So especially with control flow integrity, what you want to do is safeguard against multiple types of calls to different parts of the code. So there are some languages which might have 4 different kinds of calls and multiple different kinds of calls. At least for WebAssembly, you have direct function calls, indirect function calls, and returns. And you want to safeguard the sandbox against all of these kind of control flow integrity issues. So Wasm particularly implements function pointers through indirect calls too, where the target function of the call is contained in a statically defined table. So if you remember earlier, we had also talked about tables in this video series. This is where you have target functions of the calls stored. And typically this safeguarding process is implemented through runtime instrumentation. So what this involves is you have your compiler generate an anticipated flowchart of program execution and what the compiler thinks the program execution would go like. So you generate a flowchart of that, and then you insert checks at each call site to ensure the transition is secure. So you have sets of anticipated call targets created and assigned unique identifiers. And the runtime instrumentation verifies if the call target belongs to the expected set of call target. So if this check passes, the original call proceeds. Otherwise, you have some failure protocol, which with WebAssembly runtimes usually involves in terminating the program. There are all of these safety measures implicitly baked into the execution process with WebAssembly runtimes. And the use of explicit function section indexes we were talking about briefly, and a guarded call stack inherently secure direct function calls and returns as well. So you also have the type signature of these indirect function calls checked at the runtime and establish some sort of basic and inherent control flow integrity within your WebAssembly runtime. And all of this is established without the need for any explicit runtime instrumentation within the WebAssembly module itself. So there's no need to change stuff within the WebAssembly module. But we only talked about runtimes around this to talk about how we established this sandbox, which is particularly interesting as well. So that's how WebAssembly Sandbox and WebAssembly Memory together handle all of these issues. And at this moment, it might seem like a free lunch, but no, it's not a free lunch. So the architecture effectively prevents direct code injection attacks, but it also introduces an inherent trade-off. So you also inadvertently complicate the task of the operating system in preventing undesirable actions within the sandbox itself. So let's take a look at a few intuitive examples where this might fail and why this is not a free lunch. There are most certainly a lot of different examples and kinds of exploits that people have found that WebAssembly doesn't guard against, but we'll take a look at a few very intuitive examples. Popular problem with software systems is buffer overflow attacks, and usually what you do to get around these kind of attacks have something called a stack canary. What a stack canary does is it inserts a random value on the stack that is checked later to ensure that it hasn't been tampered with. If the value has been modified, which is randomly set on the stack, the program indicates that it was an attempt to exploit buffer overflow. So first notice that these kind of stack canary systems, which have always existed in traditional systems, these traditional memory monitoring systems are practically ineffective within the WebAssembly sandbox. And these mechanisms which detect attempts to tamper with unauthorized memory regions are unusable within the WebAssembly sandbox itself due to the strict containment of modules memory space. So this is most certainly something you have a trade-off with in terms of WebAssembly sandbox. Another thing is WebAssembly provides a level of implicit control flow integrity through explicit function section indexes and protected call stacks, as we just talked about. But it is important to recognize that the protection is not all-encompassing in the sense that there have been code reuse attacks which target indirect calls with function level granularity, and these still remain a potential threat, even though we did talk about how WebAssembly runtimes safeguard indirect calls. So there's also unmapped pages. So this is also one of the fundamental protection mechanisms in native programs. And what this involves is you utilize virtual memory with unmapped pages, and when an attempt is made to read or write to an unmapped page, it triggers something called a page fault and leads to termination of a program. However, if you think of trying to build this kind of system within WebAssembly's linear memory, well, the linear memory operates very differently. It provides you this single uninterrupted memory space without any gaps or without any unmapped areas at all. But however, due to the absence of guard pages that can be installed between static data and the unmanaged stack, and the heap overflows in one section can just corrupt data in any adjacent sections. And this can go quite unnoticed because you cannot have these guard pages at all. If you see linear memory as it is designed is inherently non-executable to prevent direct jumps to any part of the linear memory. And furthermore, WebAssembly also does not support marking any part of the memory as read-only. Hence, all of the memory is pretty much writable. And there is no idea of a read-only piece of memory. And you cannot have these guard pages that we talked about play a pivotal role in native programs. So there are quite a few problems still with the WebAssembly sandbox, but it provides this very thin virtualization layer. And this is also how WebAssembly is being used in most cases today. It's being used in embedded environments quite a lot. So even though there are quite a few techniques that you cannot run with WebAssembly memory and the WebAssembly sandbox, like stack canary and having guard pages, we talked a bit about the kind of problems that WebAssembly memory does solve.
Now, in order to understand about WebAssembly, and we have talked about Wasm module, like we have been saying Wasm module, but it's kind of important to understand what is inside the Wasm module. So we'll try to understand it not very deeply, but at least to a level where we are comfortable and we know what goes inside the Wasm module. So there are two types of representation. One is text format, which is the WAT implementation. Another one is the binary format. But in order to understand this particular section of Wasm module, we will try to see it from text format, and then we'll do a what to binary to compare it, how it looks like in binary and how it looks like in the text format. So when we talk about the Wasm modules, there are basically two sections. One is the known section, one is the custom section. So known sections are the ones that are checked at instantiation for validation, and the custom sections are the ones which are not checked at the instantiation of the module for validation. In the known section, there are different sections. So we have the first one. Even if we define no module, like we say nothing is there and it's an empty module, then also there is something which every WebAssembly binary will have, which is called the preamble. So preamble is something which is a byte aligned memory. So you can see here we are starting at 0 address and then we are starting at 4. So we have the Wasm binary magic and Wasm binary version for every WebAssembly module which is there. This is the hexadecimal representation. And we start at this memory address. So this particular thing is a byte aligned memory. Coming to different sections, the first one is the type section. In type section, we define list of all the function signatures. So all the function signatures, and this is the bot for that, you can see all the function signatures, different type of function signatures over here. Import means all the module imports. So for example, we are importing particular syscall from WASI snapshot preview 1. So any syscall that you are importing or anything that you are importing would be coming in the import section. Third one is the function. So list of all the functions. So you can see function and underscore start, and you can see the function details over here. So list of all the functions come under the function section. A table, which is used rarely, it's a typed array of reference that can't be stored in the linear memory. And memory is the linear memory of the module. So if you can define the linear memory of the module and what goes into the memory, and then you do the memory.fill. So that's the what representation of memory. Some of the other ones are start function called when you run the module, export meaning list of all the objects that will get returned to the host, and then you have global, which is the definition of the global variables, code, which is the body of each function, element that declares the data that gets loaded into the module's table, and data is the data that gets loaded into the module's linear memory. So in theory, this is what goes inside the module. Let's try to see from an example perspective and see all these functions. So this is the theoretical aspects, and you have to open your mind to understand it, like what goes inside the module. There is known section and then there is custom. So after known section, there is custom sections like name, etc. So that can become. But in the known section, we have type, import, function, table, memory, start, export, global, code, element, data, which are there. So this is the format. So you can see this particular website is called What to Wasm. And here on the left hand side, you have a what representation. On the right hand side, you have the binary representation. And you can see over here as well, it is a WebAssembly has text and binary format. This formats converts text format to binary format. So that's what it is there. And you can see the code format and the log for this, like how it works. So we have studied. So let's start from an empty one. So I told you, even if the module is empty, we have seen that in the slides before, like even if the module is empty, you will still have the preamble and you'll still have the basic Wasm binary, magic Wasm binary version and some of the other things for each WebAssembly module. And let's try to do it with a simple. So this is a simple program, and you can see it exports add to and the parameter, the function. So you can see section type. So type is having the type of the function, and then you have the function. You'll be having a section called function because we are doing a section function. And then there is a export for this, export code and body, because we have function code, we have function body, everything is over there. And then you have a section name. And this is how it is represented in binary, and you can see the hexadecimal representation of it, and you can see all the memory addresses and stuff where everything is properly getting stored. And this would be the JS representation, JS equivalent code for this instantiation of the module. And you call the exports, and then you can see the JS logs. Let's see bit more enhanced example of factorial. So again, we start from a module, we have function, we have if, else, and then we have an end. And if we see some of the sections from here, you can see first you have the preamble, then you have the type section, In that also you have func type, and then you have section function, you have an export, you have code, you have body, and you have the name. So these are the same. Coming to the bulk memory, so we can see the memory module. We'll be able to see the memory section over there. So you have type, function, and you can see here we have a memory section as well. This goes into the module. This is what a WebAssembly module is. So you can actually see, like, you won't be writing this, or you won't be writing the binary directory, you won't be writing anything of that. You will be writing the code, you'll be compiling it, but you should know what actually goes inside the module and how it is represented with the binary hexadecimal codes in the binary and how it is being processed. So that's what goes inside a WebAssembly module. Now let's talk about Wasm networking. So for most apps, you would require networking. And when we talk about Wasm, which is WebAssembly modules cannot support networking on its own due to all the security, sandboxing, and isolation. This is why you need to bring WASI. We already have learned about WASI. WASI is WebAssembly System Interface that acts as the API between your WebAssembly module in the user space and the native kernel code, which is the native code. So it acts as a bridge between them. And WASI provides you with a set of APIs. Now, what do I mean by that is there are a lot of proposals from different scenarios. For example, like garbage collection, and there is one proposal for networking as well. So there is a WASI networking proposal which is already there and has set of API definitions. Now, what happens is WASI has these proposals and set of APIs, how to fulfill certain specific tasks in a standardized way so that it is same across all the platforms. Now it's the runtime. So there are Wasm runtimes, for example, Wasm time, Wasm edge, Was0, all these are the WebAssembly runtimes. Now these runtimes implement these set of APIs. So for example, since we are talking about networking over here, so runtimes are implementing the APIs in the specification or in the WASI networking proposal with their own logic. For example, this is how Wasm time, which is one of the oldest WebAssembly runtimes, have implemented the sock, accept, and the basic networking. So this is the PR is from February 2022, and you can see it implements sock, accept, and basic networking, and there are 18 file changes in this particular pull request. So you can go through all the changes. So together, this enables the basic networking in Rust. So it has like sock, accept, all the basic networking, pre-opened socket. So whatever is required for a socket connection to be built, it has implemented that. And even if we see the file changes, you will be able to see in the source file that there are different, like sock accept, this is how the sock accept is there, and different set of implementation for the API specified in the WASI networking proposal. So you can go through this particular PR and have a look how the PR was done in Wasm type. So how the implementation of those API specified in the WASI networking proposal was done within Wasm time. So this is the proposal, and this is in phase 3, and you can see it has the introduction, and introduction means just adding the TCP UDP sockets and the domain name lookup to WASI. It extends the BSD socket surface with the intent to enable the server and client networking running on WebAssembly. So the proposal includes 4 new WASI modules, and you can see that over there. And you can see the goals to enable the basic functionality of TCP UDP application and some of the non-goals over here. And then you have the API walkthrough and some of the things that you need to implement, and also the WASIX compatibility over here. So you can go to the WASIX compatibility at application level. So if we talk about like basic applications, you might want to invoke TCP IP connection, you might want to invoke a web server, you might want to connect to a database. So all these are the applications where you would actually need networking enabled. Another runtime which we will see a lot of demos is Spin. So Spin is an application framework for WebAssembly. Spin also implements socket connection, like connecting to the KV store, which we'll demo later in the course as well, on the bare minimum. So on the bare minimum, when WASI runtime wants to implement WASI API for networking, the most basic thing is to open a socket connection. For example, if you have a guest module, so by socket connection, you can enable the connection to the web server or database or whatever, and Wasm runtime starts that connection based on its own implementation instantiated by the guest module. And specifically, there are certain things like sock bind, sock listen, as you can see on the screen. So it's socket. So you create that, and then you have bind, and then you have listen, listening for it, and you accept. And on the client side also, you connect to it, and then there is, once the connection is established, it blocks it, and then you have the read write, and then you close it. So this is how it actually happens. And what I'm going to show is whatever you are seeing on the screen right now, all these, how they are done. So we'll use a simple C program and see some of the syscalls over there. So we have a file over here. Let me open that. So in this example, it's a 2-player example, and you can see at first it's creation of the socket. So you can see socket opens the file descriptor and the stream. So that's what AF, INET, and sock stream would do, listening to the stream of arrays or stream of bytes over there. And then once this is done, initializing the server address, and you can see after this, we have the second step that we saw in the diagram was of the bind. So you bind that to the socket address, and after that you listen. So you can see setting up the queue in the kernel to hold the pending connection, and then we create the accept. We have 2 players, so we have created 2 accept. So that is the accept for the socket, and then there is a read write when the play is going on. Now here, what we are using is we are using the sys socket. So we are using the system calls for that. So GCC, and we give Lego, it generates a dot out. So we'll just do run a dot out, and it's listening on 4, 5, 3, 2, 1. So we will netcat. So you can see you are player 1 waiting for player 2. And if we go to another terminal and we do a netcat, you will be able to see you are player 2. So now the connection has been established, and welcome to the chocolate Lego block game. And there are 10 Lego pieces, whatever that is. So you can see connection has been established, and that's why it is that. I think with this, it shows the entire process that I wanted to show for this particular WASI networking, how it is, being done of creating a socket. And that's what is defined in the WASI APIs, and that is what is being implemented in kind of a similar manner, just like we have done here. It's a very simplified version, but the runtimes, they are done according to WASI and specific more set of features which are provided. One more thing which I wanted to show is WASIX. There is networking and it is there, but when you talk about multicast, when you talk about IPv6, when you talk about more complex networking which is required, so WASIX is something which has full support of sockets. Now, what is WASIX? So WASIX is a long-term stabilization and support for existing WASI ABI plus additional non-invasive syscall extensions that completes the missing gaps enough for the real world applications. So it's basically termed as a superset of WASI. It might not be as per the WASI specifications, though it has already implemented the WASI specification, plus it has its own set of features to provide all these things like multi-threading, asynchronous support, file system support, sub-processes, browser support, TTY, runtime support, all these things. And for now, it is only being supported as Wasm Runtime. WASIX supports the Wasm runtime. That's how it is being done. It is actually built by the folks who have built Wasm, and you can see there is like the documentation over here, and you can see developed by the Wasm team. And one of the most interesting thing over here is to have a look at this statement. WASIX is a transformative design to make more compatible with POSIX program for the seamless execution of more complex application browsers and serverless environments. So all the critical missing POSIX features in WASIX allows the developers to use WebAssembly. So it's basically, they did this to make sure more and more people can adopt WebAssembly, although most or the extensions or whatever they call it, they are not in the WebAssembly like the Bytecode Alliance standards, the WASI proposals. So WASI proposals is there, and they have termed it as WASIX, making it like WASI is there and it is compatible to that, but they have enabled more set of features on it. So you can see WASI Preview 1, and then it's a superset of WASI, which is having more number of features, and they call it as an extension of WASI. You can also check out this project if you are looking for advanced networking or some of the features which are not there in some of the specific runtimes with respect to the WASI specification for networking, which is already out there. And this is the core WASI API proposal for managing sockets. So that's pretty much it for the WASI networking.
So now let's talk a bit about the tool chains around WebAssembly and the kind of tooling we have around WebAssembly to build WebAssembly modules, compile it down to WebAssembly, and run it in other kinds of languages. This tooling should particularly be very strong because we are trying to run arbitrary code in arbitrary languages. So we would essentially want a very strong tooling around WebAssembly to make all of this run seamlessly. So let's start by talking about WebAssembly runtimes. And all of your WebAssembly code is being run by a WebAssembly runtime under the hood. And all of their Wasm features also depend on runtime implementations. So, for example, let's take a look at the WASI spec. And you might find this very familiar if you might have used C or POSIX. And WASI has very similar names for system calls. So, WASI defines this spec, and WASI tells you that what kind of inputs it expects, what kind of functions does this do, and then our WebAssembly modules can use this spec. We haven't talked a lot about WASI yet, so right now you can just understand it as a way to be able to run WebAssembly modules on all kinds of platforms. So you'd probably have different system calls on each platforms, and WASI just allows you to do so. We'll talk a lot more about WASI in upcoming sections, but this is just a brief review of it, just to set some context for what we are seeing over here. So WASI shows me the spec and tells me what to do, but it is up to the runtime to implement this. And to this extent, you could also have runtimes that, for example, implement the sandbox in a very different way. You could have a runtime that takes a Wasm module and runs the Wasm module, but gives it full access to the system software. And you might think, doesn't this violate like all that we have been talking about sandbox? Or does it very differently? And well, it does. And all of this is up to the runtime. So runtimes are responsible for this implementation and making sure all of the Wasm features are properly implemented. Let's talk about WASI libc as an example. So we already talked about quite a few of the compilation steps and saw how any code is compiled down to WebAssembly. What WASI libc does is it just gives you an interface for all of libc functions. So you can use them while making your WebAssembly modules, and you can compile C code directly to WebAssembly. So WASI libc is usually distributed with the WASI SDK. So you have Clang with the WASI SDK that compiles the C code into LLVM IR, and LLVM applies optimizations to the IR, which is then converted to WebAssembly, and then you load the LLVM IR to Wasm instructions. And then you can also have any object files that are generated, and those will be linked together using the LLD linker. So we'll talk a lot more about this in upcoming sections, but this is an overview of how WASI libc does this. And then you have a linker. There used to be multiple projects like WASI linker to do this kind of stuff, and now they have been distributed out of the box. But you essentially also have a linker that links the program with WASI libc, ensuring that the standard library functions you use in your C code, any system calls you use in your C code, are properly implemented according to the WASI spec. So we saw an example of the spec, and if you had that kind of call in your C code and you wanted to lower it down to WebAssembly, you need to do a few things to make sure that function is properly implemented according to the WASI spec. What WASI libc usually does is it has these two parts. We'll talk about this in a lot more detail, but over here we are particularly talking about this in the context of Wasm runtimes and giving you an example of how different things in Wasm runtimes usually work. So that's why we take one of the most popular examples, WASI libc, and talk a bit about it. We don't talk about the WASI parts very specifically just because we are here to talk formally about WASI. You can roughly divide WASI libc into two things. So you have like the WASI libc bottom half. And what the WASI libc bottom half does is it's just the lower half of a traditional libc implementation. So that consists of C interfaces to the low-level WASI system calls. So this implementation also includes something called the pre-open functionality. And what this does is this just emulates the POSIX APIs, accepting absolute paths by translating them into pre-opened directory handles and relative paths. So if you recall, this kind of stuff can be done with OpenAT. So WASI libc particularly takes inspiration from libpreopen to do this kind of stuff. And what the top half of the WASI libc does is the upper half of a traditional libc implementation that consists of C standard library and other high-level functionality. So that's how WASI libc is structured, and that's how different runtimes can use this kind of functionality. This would particularly make a lot of sense if you have written code in C earlier. Even if you have not written code in C earlier, you might have gotten a bit of an idea of how the linking process happens and how WebAssembly runtimes use this. But if you have not coded in C earlier or have not used POSIX APIs earlier, it's completely okay if you don't know all these specific system calls that I was talking about. Okay, let's come back to WebAssembly runtimes. So when a WebAssembly module is loaded, the runtime first passes the binary format of the module. And let's take a overall look at what the runtime does to run this WebAssembly module. So you of course first pass the binary format of the module, and what you also do while doing this is break down the binary code or the binary format in which a WebAssembly module is into a structure that the runtime can understand. The runtime also performs validation to ensure that the code adheres to WebAssembly specifications. So things like type safety, unmapped memory addresses, which you can already catch them at the load time. We already talked about how a WebAssembly module is structured and what parts of WebAssembly module can respond to what parts. So this particularly makes a lot of sense if you remember about that. So WebAssembly module can usually be executed in two ways. You have something called ahead of time compilation, and that's pretty common. So what you can do is use the WebAssembly bytecode, compile it into some native machine code before it is executed, and this is very similar to how a traditional compiler works, right? You translate the WebAssembly instructions into instructions that the processor can execute directly. And you do this with different kinds of languages already. So you can also do ahead of time compilation if you want. And this, of course, also requires you to let go of the universal compatibility that you can run a WebAssembly module anywhere you want to, because once you generate an AOT, it becomes specific to the architecture, not specific to the system. The other thing which we do a lot of times is JIT compilation. So the runtime can use a JIT compiler that converts the WebAssembly code to native code on the fly as it is being executed. And this approach allows for optimizations that would be based on the runtime behavior of the code. So there are quite a few optimizations you can also make. Also, this does depend entirely on the runtime. So you could have a runtime that let's say interprets the WebAssembly code directly and executes all the instructions here step by step without compiling them into machine code. So you could do this with a runtime, and there are a few WebAssembly runtimes that also do interpretation. So this all depends on how a WebAssembly runtime is structured. So once you have the WebAssembly code is compiled, it is then executed, and the runtime manages the execution. It ensures that the code adheres to the constraints of the WebAssembly sandbox model that we were talking about. And it also manages the memory access, handling calls to and from the host environment, and enforcing the security boundaries that we were talking about. So usually what happens is WebAssembly modules can only interact with the host environment through a well-defined interface. And this interface includes functions that the WebAssembly code can call to perform tasks. So we particularly saw an interface in the snippet of the WebAssembly system call spec that I showed you. So the WebAssembly runtime most certainly does this when you run our WebAssembly module. And the WebAssembly also has a linear memory module. And the runtime is responsible for managing this memory, which includes allocating and freeing memory as required, making sure that it can only access memory within its range, and finding out if it's trying to access memory which is not in the range. So all of this is also handled by the runtime. So now let's take a look at some of the tooling around WebAssembly in action. So we'll take a look at all that we talked about in the video. We'll take a look at compiling WebAssembly modules and then running WebAssembly modules in some runtime, and also running them in embedded runtimes. So we'll take a look at all of that. We'll take a few examples. So let's first start out with using WASI and WASI. So I have some C code over here, and all of this is pretty standard C code if you look at it. I use system calls like open, read, write. So all of these are pretty standard C system calls or POSIX system calls. And I can use them just as I would write any C code. This particularly is some simple C code to copy a file from one place to another. So I have a from path and then a to path, and this copies a file from one place to another. So this is just some C code to do that. And there's nothing specifically in this C code that's for WebAssembly. All that we want to do is when we compile this C code, we want to compile it down to WebAssembly instead. So let's take a look at how one can do that. So first what we'll do is we'll use WASI libc from the WASI SDK. I have WASI SDK installed. So first set up the pod to WASI SDK. In my case, it's this pod. So WASI SDK and WASI libc also give me a modified clan. So I can give a path for that clan just so I could use it later on. I have this, which is a modified version of clan that supports directly compiling it down to WebAssembly. And also need to pass the sysroot, so let's just do that. And now, just as I would for any clan compilation, just compile the C code we had. But I compiled it down to .wasm, so I have a copy files .wasm, that is what I'll compile it. And there we have it. So let's just take a look at copy files at Wasm. And this is indeed a WebAssembly binary module. So we were able to compile some C code to WebAssembly. And what we can now do is also run this with the Wasm runtime. So under the hood, when we are compiling the C code to WebAssembly, we are following all the steps that we talked about earlier. And now let's try to run it with a WebAssembly runtime. So we also talked about this, and that is what we'll try to do. I have something called minus minus mapdir. And what the minus minus mapdir does is it tells the WebAssembly module what directories it has access to. So here I give it access to my current directory and place it at the WebAssembly module's current directory. For this example, I use Wasm time, which is one of the most popular Wasm runtimes out there, but you can use your favorite Wasm runtime. I have this file called random.txt, and I'll just copy it to random2.txt. Let's try doing that. We can rewrite mapdir and interesting. So now we can see that random2.txt does indeed exist. So now we just saw how we can compile C code to WebAssembly and then run WebAssembly code with runtime. And all of the tooling around it makes it really simple to do it. We abstract all the steps that we talked about earlier in the video. And now let's take a look at a Rust example. Rust has a lot of tooling around WebAssembly pre-built in it, so we can very easily start working with Rust and WebAssembly as well. So let's take a look at some Rust code that we have. So this is the Rust code to the same end. It uses stdio in Rust, so there's nothing specific in this Rust code as well for WebAssembly. And this just copies a file from one place to another. So let's try this out ourselves. And right now I already have a random2.txt, so let's just this. So first what I can do is use Rust sub target art. And what this does is install support for the wasm32-wasi target, because this is what we'll be compiling it down to. Now what I can do is simply do a cargo build. And because we want to compile it down to WebAssembly, we can also pass in the target to wasm32-wasi. And this will build it for us. This is pretty quick. Let's take a look at what it has produced for us. So target wasm32-wasi release, and our file was called copy files -rs.wasm. So this indeed produces a WebAssembly binary module as well. So we can run this WebAssembly binary module as well, and it will produce the same output as we saw earlier. But the tooling around Rust is also very simple for anyone to start using right out of the box. A very common use case of WebAssembly is running it in embedded environments. For example, writing a WebAssembly module in C like we did, and running it in, for example, Python or any other language. So this is one of the most common use cases for WebAssembly. So let's take a look at that. I have some Python code here where I use another Wasm runtime called Wasmer. Wasmer is also a very popular Wasm runtime, and it has a lot of rich SDK support. So you have SDKs for Wasmer in almost every language. So I particularly use Wasmer to run the Wasm module that I had. I start by opening the Wasm module and creating a store for the Wasm module. So right now you might have some idea of what a store for a Wasm module is, but we'll talk a lot more about this later in the video. We'll then, as we talked about what we need to do when running a WebAssembly module within a runtime, we'll then compile the WebAssembly module. And we'll also say that we want to use WASI while running the WebAssembly module. So I also say that I want to use WASI, and I give it some arguments, which are the arguments I give to my code. And I also have this path which says map directory. This is same as what we had seen in Wasm time. We give it access to the current directory, and then WebAssembly modules, as you might recall from earlier, have things that they import or export. Functions that are exported or interfaces that are exported through the WebAssembly module are the ones that the host can call. we particularly want to call some function which a WebAssembly module exports. By default, a WebAssembly module with the WASI SDK or even with the Rust compilation creates a function for us called underscore start. This is the default function. We could also call other functions if we had them. In my case, let's take a look at the C code we had. We had this main function, which is what we want to call. So by default, WebAssembly does create an underscore start function for us. So we'll just call that. And you could also have different functions that the WebAssembly module exports, and you could call them. So let's take a look at running this. So I then remove the random2.txt because that is what should be overwritten over here. And now let's try running the Python code that we have. And this indeed worked. And I have a random2.txt as well. So we just took a look at compiling WebAssembly code, running it in embedded environments. And this is the tooling around all that we talked about that happens under the hood.
Up until now, we took a look at running WebAssembly on the browser. And that's very good how we can run WebAssembly modules on the browser. But let's take a look at thinking about how we can run WebAssembly outside the browser. And up until now, what we took a look at is we have some Python, C, Rust code, or whatever language we have, and we convert that to a WebAssembly module. And finally, we will be running this WebAssembly module. This conversion has quite a lot of steps in it, but right now, just say we are going from a source code to the WebAssembly module. And this WebAssembly module then requires some JS glue code to be able to run it on the browser. So this is what we used to do when we wanted to run WebAssembly on the browser, and we already took a look at that. When running WebAssembly beyond the web, we still want a scalable and secure way to run the same code across all machines. A lot of stress on the same code across all machines. And if you think about it, the browser has a limited set of capabilities of what it can do and what it can't do. So there will potentially be new challenges in running this in a secure way beyond the web. What I mean by being safe and portable is we want the users and programs can do what they have the right to do and not create problems for any other users. And this also works for WebAssembly modules. So what we want to try and do is have standard platform independent methods to do this. And we also want it to be platform independent. So the same WebAssembly module can be run across all kinds of devices. We did not have to think about this in the browser because it did not have the set of capabilities to interfere with other kinds of programs. And often wherever the web browser was being run would often handle that for us. So now we need to think about these new challenges which come when we try to run WebAssembly beyond the web. Another thing we want is binary compatibility. So this is a big set of fairly straightforward wants, and these also make sense just because of the WebAssembly promise we talked about. So we want all these set of things when we try to run WebAssembly beyond the web. So first, let's talk a bit about system interfaces and how system interfaces come into play. There are different protection rings, and so we can only have the kernel talking to the device drivers. If let's say any applications want access to the system resources, they'll talk through the kernel, and the kernel will allocate system resources for them. So this is how Linux uses protection rings, and the way this happens is the way applications talk to kernel is through system interfaces. So we have the applications, and these make system calls to the kernel, and the kernel then has access to hardware resources. So the kernel can allocate these hardware resources for all the applications. So this is how system interfaces come into play. This is also what almost all applications use. System interfaces for each architecture or for each target will be rather different. So let's say you have some C code and you try to compile it down for a particular target or for a particular, let's say, microcontroller. So the way system calls would be done on that would be rather different than something else. And if you want to do system calls to access hardware and access other kinds of resources. So this is why getting portability is not such a straightforward problem to solve, because system calls on each architecture and each target would be rather different. So this is also how standard programming languages like C are compiled down to. So they use system interfaces or system calls from the particular architecture or the particular target you are compiling it for. Now, for WebAssembly, this is a bit different. We don't know what target we'll run it on. As we talked about, system interfaces for all targets can be rather different. So this is something to think about. First, of course, you might remember how Java does it, which is rather popular. So what Java does is it has a Java virtual machine. Whenever you compile down something, it's compiled down into something the JVM can read. And then when you try to execute the Java program in real time, the JVM uses the combined or intermediate code and runs that. And this is now portable across all things because the compilation process just needs to take into account the way JVM does system calls, and then JVM does it for other kinds of architectures. So this is kind of the first thing that comes to mind. And this is also very similar to what we'll soon be talking about. So it does make sense to do something like the JVM and at least take inspiration from JVM. That seems something likely. So we'll explore how we can do something like this pretty soon. So let's take a look at system interfaces. So what I've just done is I listed all the system interfaces that is required when you run a list command. And you also see OpenET there. So system interfaces are definitely useful for the file system or using any of these resources. Now that we talked about a few of the things we could think of about how we could run WebAssembly. So one of the earlier ways this was done is using mscripten. So mscripten was originally for running WebAssembly on the browser. But an ideal way to take this forward would be you could probably emulate a browser on some host device and still use mscripten. What you would be doing is have a WebAssembly module that still runs in a browser, and the browser is being emulated across whatever device you want to run it on. So you still get to, in your application or compiling to WebAssembly, you still get to be able to work with the standard set of system calls, but it can run everywhere. And essentially your runtimes will now re-implement the JS glue code, emulate a browser. So this was one of the earlier ways that WebAssembly was run beyond the web quite a few years ago. And this also made sense just because of the way we talked about running WebAssembly on the web. So this approach also was a natural extension of what we would be able to do. A problem with this approach is you think about the WebAssembly module and then you think about emulating the JS glue code and emulating a browser, and the emulated browser then talks to the kernel, and then the kernel gives resources to the emulated browser, which then in turn gets us resources for our running our WebAssembly module. So this already looks quite hacky, and truth be told, it is quite hacky. It also turns out to not be performant enough, but at least at the moment we understand how WebAssembly was run beyond the web in the older days, and why this kind of approach also makes sense to think about. So later we'll take a look at how you can performantly run WebAssembly beyond the web, and we'll also introduce something called WebAssembly System Interface. So earlier we take a look at WASI, or WebAssembly System Interface. In this video, we'll take a look at demos with WebAssembly System Interface. Particularly, we'll be taking a look at two demos with WebAssembly System Interface and Wasm. First off, we'll take a look at a very simple hello world example, and then a more complex example where we want to write down files, and read files, and interact with the file system. So let's take a look at that. First off, let's take a look at a Rust example. I also have more examples over here, so feel free to go through them. I'll not go through each and every one here. As the name suggests, this is a very simple Rust example. All this does is prints out hello world to std out. And this does this in a loop and then waits for a second. So this is pretty simple and fairly straightforward to understand. Now what we'll do is compile this with Wasm plus WASI. So let's get to doing that. First, I'll add a target. I want to compile this for Wasm 32 minus WASI. So I can use Rust up to add this target.
So let's do that. In your case, if you do not have this target installed, Rust may also install a few things. Now that we have the target added, let's move to where our Rust project exists. And now I can simply do cargo build. You might have seen cargo build earlier. And this is pretty simple, but all I'll do is just specify the target as wasm32 minus WASI. Oh, that is pretty quick. And it says it has compiled it for wasm32 minus WASI. So let's take a look at the Wasm Module it produced. So that should be in target. Wasm32 minus WASI release. And my project was called Hello World minus RS. I compiled it, so it should be called Hello World minus RS. So yeah, I do have a Wasm plus WASI WebAssembly module over here. Great. Now, if you remember from the earlier videos, this is a Wasm plus WASI module. So I can run it simply with any Wasm runtime. And I don't need any JS glue code. I just need this Wasm module and I can run it. That was the whole idea of WebAssembly and WASI. So let's try that out. I have Wasm time. You can choose your favorite Wasm runtime. So I can just do and run this with Wasm time. And hopefully this should print out hello world a few times, well, infinitely in a loop, and wait for a second before each of them. Great, so that did work out. And let's also take a look at the WebAssembly text format that this produces. So you can produce WebAssembly text format with a bunch of tools. There are quite a few tools to do that. There's also Wasm tools that allows you to inspect and create WebAssembly text formats from these Wasm modules. You can also run the WebAssembly text format with any of these Wasm runtimes as you may have expected. So yeah, let's take a look at the what that we have. This is the WebAssembly text format we produced. And I particularly want you to see that this does use the functions or methods that the WASI spec had. For example, you see fdwrite over here. So this does use the underlying WASI methods. So fdwrite is actually the one that will print something out to std out. And you see that it actually does the print over here. So indeed, this is using Wasm plus WASI under the hood. Now let's take a look at a more interesting example. We'll take a look at an example where we do this with C. So first off, let's see what we have. This is my C code. This is also fairly straightforward to understand. And this tries to replicate some of the capabilities of the Linux command cp. This copies a file from one place to another. As simple as that. And there's nothing different about this C code. There's nothing which is like specific to Wasm plus WASI. It's just normal C code that you'd write. Normally, how you'd copy files, how you would write out files, how you read files. So there's nothing different in the C code. What we can observe is that it makes use of the file system. So for example, it tries to read from the file system, and it then tries to write to the file system. As expected, CP should do that. So we'll take a look at how this works with the context of Wasm plus WASI, because we earlier also talked about Wasm Sandbox. And ideally, my Wasm modules, when running, wouldn't have access to the file system. So let's also take a look at this and how Wasm plus WASI comes together with Wasm Sandbox. We'll take a look at that in action. We already talked about it in previous videos. So let's take a look at that in action. I have a version of CLang, and all that does is when you ask it to compile, well, it uses Wasm plus WASI, the compilation process, and produces .wasm binary. Great. So let's do this. So first off, I have WASI SDK to do this. WASI SDK is a collection of tools. One of the tools it has is CLang, well, modified CLang to do the compilation process. So first off, I'll just set a few things, and I want to set the path to my WASI SDK. So let me do that quickly. Well, I have the latest version of WASI SDK at the moment of recording this video. So I'll just pass in the path to WASI SDK. What I really want to use from WASI SDK is one of the tools. The tool I want to use is CLang. So I can just make a utility for it. And I'll also pass in the sysroot. I can do that. And WASI SDK also gives me that. So this already assumes that you have WASI SDK installed. There are quite a few installations that we assume you to have already installed, which are in the company GitHub repository. So take a look at them. Now I have this utility to compile my C programs, and let's see this in action. Let's try to do it for compiles. So I called it compile.c, and I'll also pass in the module I wanted to return out to. So I'll just make a new one and call it copy files minus c.wasm. So I made a minor typo over here. I wrote it as Bing. So let's change that to bin. Great. And now let's compile copy files.c. Okay, so it has actually compiled to Wasm plus Wasm Module. And let's take a look at what it has produced. So this does say it's a WebAssembly binary module. So let's try running this. And again, this is a Wasm plus Wasm module. You don't need any accompanying JS glue code, and you can run it with your favorite Wasm runtime. The way we took a look at running this with WebAssembly earlier was passing in Wasm time and then giving it the Wasm module we have. See our C code. So our C code also takes like 2 command line arguments, right? So let's also pass in the command line arguments. And my command line arguments say from and to. So I'll also pass that in. I have a very simple file over here called random.txt. And this is just to demo printing something. It has some text in it. Great. So let's try doing that. And let's try running this. And I also need to give it 2 command line arguments. So I'll just say random.txt and I'll call the other file random2.txt. And this should copy it. Well, it says no such file or directory. Can you think why this might happen? So this is expected, right? The Wasm sandbox is an action. It does not allow me to give it access to the file system itself. So we expected this, and now we explicitly need to give it access to some directory and allow it to read and write files from there. So let's try that out. The runtime where our WebAssembly module is running in the Wasm sandbox will now also have access to the file system. So let's try that out. And I'll just pass in -. So that gives us access to this. And then I can just try doing the same thing. So copy files -c.wasm. And then I have the random.txt. I'll copy it down to some random2.txt. And that would have worked. And yeah, that does work. So we also saw how WASI and the WebAssembly sandbox all work together. So that's about this area. In the previous videos, we took a look at WebAssembly system interface or WASI, and we intuitively took a look at why it's needed. It may appear as a very rudimentary solution, so to say, at the moment, or a very simplistic solution, and it might not be very clear how it fits into the whole WebAssembly ecosystem, or even it might not be so clear yet about supporting all kinds of different modules and all kinds of different applications that people might want to compile down to WebAssembly. So at the moment, those might come off as a few things with WASI among others. So what we actually took a look at was the preview 1 version of WASI. The preview 1 version of WASI, if you think about it, it was just very close to an operating system layer. But then as the community progressed and we needed stronger set of tools and also structured tools around WebAssembly, it became pretty clear that having WASI preview 1, like we talked about, would hit some pretty big limitations. And if WASI truly wanted to live up to its stated goals, it would somehow need to change. We still want everything which we talked about in WASI Preview 1 or WASI, as we talked about in previous videos. So we still want those things. We probably want to do it pretty similarly because that seemed a pretty nice or decentish way of doing things. So we want to do it pretty similarly and still need the same goals. But just having like this virtualization layer, which is very close to the operating system, might not solve everything. So we did have a few problems with WASI Preview 1. And which is where, as you might have guessed, WASI Preview 2 comes into place. In this video, we'll actually talk about WASI Preview 2 and WASIX. If you're around the WebAssembly community, you might have heard both of these terms quite a lot, especially at the moment of recording this video. These were quite popular and quite hyped up. So we'll talk about these, and it's pretty simple to understand about them now that we know about WASI. So let's start by talking about WASI Preview 2. So what WASI Preview 2 does is just think of it as like a rework of WASI, and it allows you to do WIT, something called WIT, WebAssembly interface types, allows you to work with Wasm components, and allows a variety of new standard interfaces. Now, we talked about two things, WIT and Wasm components. So you'll see that mentioned quite a lot because that is one of the solutions to having like the structured tooling around WebAssembly. We haven't really talked about it formally yet. We'll talk about it in a lot of detail in upcoming videos, especially about WIT and Wasm components and why we even need them. So I'll just say keep in mind about Preview 2 and how Preview 2 is built around to support Wasm components. And when we talk about Wasm components, do remember Preview 2 back again. So WASI Preview 2 allows you to use all of use Wasm components and use this new standard system interfaces. But what it doesn't do yet is provide first-class parameters for common things like async or just doing multi-host or some kind of distributed linking of programs. So those are yet to come. And if you see like just the Wasm community or discussions around the WASI community, that's supposed to land in Preview 3. Because a very important problem, even if you do have like the structured tooling, is even with Preview 2 or even with previous Wasm plus WASI solutions, it wasn't possible or it wasn't very easy to have one module interact with the memory from the other module. So that was a bit hard. And this especially makes things like first-class async primitives and multi-host linking a bit of a challenging problem. The way WASI is structured is that you can have nested virtualization layers. So what you can do is, let's say, have some parts of your system run in WASI Preview 2 or upgrade from WASI Preview 2 to Preview 1 to Preview 2. What you could do is have some kind of shim that allows Preview 1 code to or WASI code to continue working in hosts which only implement WASI Preview 2. So it also works pretty well, and you can think of it as just like this virtualization layer. Well, all of this is towards the goal of having a WASI 1.0. So let's take a look, a very rough overview of how Wasm Time implemented WASI Preview 2. Wasm Time also has quite a few interesting examples on using Preview 2, so I'll most certainly say look out for that. This seems like a quite a big diagram. Let's take this step by step. So a very important thing to remember is that WASI Preview 2 is built on top of both the component model and core WebAssembly specification. So you can think of this diagram as everything that's coming to WASI Preview 2 and also what Wasm Time already implemented. This is also taken from the Wasm Time docs. So you can just see that first you have the core WebAssembly specification, and this would have quite a few things like the core Wasm threads prototype, Wasm GC, which is partly here, and core Wasm thread shipping, which probably comes at some later stage. So you have this core WebAssembly specification layer. And then you also have the component model specification. This is mainly around handling widgets, making component instances, component definitions, and those aspects. And then you have the WASI layer as well. And the WASI layer also interacts with the component model. So you can see that you have like these interfaces which have been adapted to use high-level types, which would then be defined by your component model. So just a rough overview for you to understand these arrows from component model to WASI right now is component model allows you to specify interface descriptions and specify a grouping of interfaces. We'll formally put this together a bit later, but right now just understand it as defining interfaces and defining some grouping of interfaces. So what you can see with these arrows is you have like interfaces which would be adapted to use high-level types or even new custom types that are defined by the component model. And these would be defined by something called WIT, and WIT is like this interface description. And this would also include components like WASI IO, WASI sockets, WASI blocks, WASI random, WASI file system, all the ones you see over here. So this is how it essentially comes together. You also have the core WebAssembly specification, you have the component model, and you have WASI as well. We particularly take a look at, especially this part which is highlighted right now, how component model interacts with WASI, how the linker comes into play. We'll talk about those aspects later. This is what WASI Preview 2 proposes. With that, let's take a look at WASIX. So WASIX is along the similar goals of having improved tooling and better tooling around WebAssembly and WASI, but it takes a bit different approach. This figure taken from WASIX is a nice representation of it. WASIX is a superset of WASI, or more succinctly, a superset of WASI Preview 1. So you also have some kind of backward compatibility with WASI code base. So WASI code should still compile against WASIX. WASIX is just like a superset of WASI. So that should work well. And hopefully there will also be some forward compatibility with WASI Preview 2 and later when WASI Preview 3 come out or WASI 1 comes out. Mainly what WASIX does is, or the goal of WASIX was originally to provide minimum capabilities for people to compile their apps. And there were quite a few things which were missing to compile down all of these apps to Wasm plus WASI. So WASIX wants to expand the capabilities of WASI, have support for more kinds of apps which can then be compiled down to a WASIX. And one of the things that they work with is introduce support for something as simple as the fork system call, and which wasn't there in WASI Preview 1. And I remember seeing a very interesting open source project where someone had built a bash with Wasm plus WASI. And that was made a lot easier because Bash usually relies on fork quite a lot to execute all the commands. And having like these minimum capabilities is really important to build all of these basic applications or start compiling any useful applications. With WASIX, what you have is your application binary additions are frozen when published, and then those would be served by different runtimes you have. So if you take a look at all that WASIX has, it has support for networking system calls like socket, bind, and connect. You can build HTTP servers to Tokyo stuff a lot more easily. It also has browser support, which is also pretty interesting. Yeah, this is, we were just talking about fork and vfork, which is also some of the system calls that WASIX introduces with WASI. You also have a ton of other useful system calls for multi-threading and asynchronous runtimes. So that's what WASIX does, and that's what WASI Preview 2 does. So hopefully now you can better understand how these improve the tooling around WebAssembly. And in later videos, we'll take a look at something we talked about quite a lot today, component model. We'll formally take a look at that in some of the later videos.
As we mentioned that in this course, we'll be touching on the cloud native aspects of WebAssembly and where and how it all started for the cloud native community to get hyped up for WebAssembly. I think this particular tweet that I'm showing, or X post, you might call it now, is something which is very significant and that really brought up a lot of things around the cloud native WebAssembly thing and setting up something which in future actually happened. So in 2019, so this is the time when the first blog was published with respect to WASI. Like, WASI is coming into the picture now. What WebAssembly system interface will be able to do, how basically you will be able to access the file system using WASI for the WebAssembly module that you want to run on the server side of things. This is where Solomon Hykes, founder of Docker, tweeted. Now, this is important because Docker has laid the foundation for the containerization era, or accelerated the adoption, whatever you want to call it, with the ease of the developer experience, and then lays down the foundation of Kubernetes, becoming the default container runtime over there for a long, long time. So coming from Solomon means a lot because he developed a certain technology, and here in this particular tweet, and it's a very popular tweet, like everybody on the server side of WebAssembly almost knows this particular tweet, and it has been said at various conferences, so it had to be included in this course as well. So as you can see, it's for March 2019. If Wasm and WASI existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server side is the future of computing. A standardized system interface was missing. Let's hope WASI is up to the task. Now, this is very, very, very important because it's coming from Solomon. I mean, just imagine if Docker was not there. So that's how crazy it is. But obviously, since it came from Solomon, so there were speculations and there were lots and lots of questions, maybe in your mind too, if you are watching the video. Like if WASI is there, then should we start considering or replacing Docker, or is Docker getting abandoned all at once? But that's not the case, because in subsequent post he mentioned, so will Wasm replace Docker? No, but imagine a future where Docker runs Linux containers, Windows containers, and Wasm containers side by side. Over the time, Wasm might become the most popular container runtime. Docker will love them equally and run it all. Now, the fun thing is, this tweet is from 2019, and moving fast forward to October timeframe 2022, Docker released the preview support for WebAssembly containers, which means you can use the same Docker CLI tooling, the Docker desktop, to actually create WebAssembly containers, which are the OCI artifacts, push them to Docker registry, use the Docker run command to run them. I mean, this is the thought leadership. Someone who created a fantastic piece of technology, appreciating another fantastic piece of technology out there. And this hyped up a lot in the cloud native ecosystem, cloud native community. And eventually it became the truth. Like in 2019, he just predicted it will happen. And it actually happened in 2022. And that's where the real acceleration happened. Because now the thing is that you have the same tooling. You have and you can use the same tooling that you have learned over the years to even run WebAssembly or create WebAssembly modules. So that is a very significant milestone when we talk about WebAssembly and cloud native. Now, when we talk about the cloud native ecosystem, obviously we cannot skip the containers part and the Docker part in that. Also, when I explained the Docker thing that, Solomon Hykes tweeted so and so things, and then Docker announced its preview support, let's try to understand first the difference, like people saying that WebAssembly is replacing Docker and stuff like that. So let's try to compare WebAssembly and Docker. So as you can see, the Docker, which is installed on your host operating system. So basically you have your infra and you have your host operating system. On top of that, you install Docker engine, and then you have your applications with its libraries and dependencies deployed as containers. On the other hand, when we talk about WebAssembly, so you have the infrastructure, host operating system, and then you have the Wasm runtime, Wasm edge, Wasm time, etc. And then you are running the WebAssembly module. And for any of the interactions that is there with the host is done using the WASI layer, which is the WebAssembly system interface. So that's how it is done. So let's try to compare it. Speed-wise, yes, Wasm is much more faster due to the smaller binary sizes and instantaneous startup times. So it's pretty fast as compared to Docker containers. It's smaller than the Docker containers, like it's in few MBs, and the Docker container might be in, multiple tens of MBs for the same module that you're trying to run. WebAssembly module is the compiled binary that you are running in the end, whereas on the Docker hand, you have its dependencies, library. It's a whole ecosystem. Like it's a virtualized operating system layer that is there. You can exec into it, and you should be able to see all the bin, all the other folders as well. Portability wise, Wasm module is platform agnostic. That means you can run it on any system, irrespective of the architecture. But the Docker containers are architect specific. So you have to make the Docker containers separately for different set of hardwares, and certain set of hardwares do not even run, like Windows, Linux, those kind of mix and matches won't happen very easily. So I think those are some of the features where we can differentiate the Docker and the WebAssembly ecosystem. But I think it's more than the differentiation. Like I just brought it over here since many people think the Docker and the WebAssembly ecosystem as something it is replaceable and things like that. But I think they both go well hand in hand. Like for long running processes, you have Docker containers, and for short lived, you can have the WebAssembly modules which are there on the components. This is even more interesting. So Docker and WebAssembly. So Docker announced the preview support in October 2022, and since then it has been increasing its support, making it more stable and stable, adding more runtimes to it, and it is done using the run WASI layer. So basically the request, how things run here is, So when the request comes to Docker, it passes that to container D, and it says container D, hey, run the container. But container D also doesn't start the container. So it actually passes through the container D shim and goes to the run C. Run C is the low-level runtime that starts the container, and then again via the container D shim, it passes on the status to the container. So that shim layer is now replaceable, and it's now a container D project called Run WASI. So in that now, if you have the Run WASI shim, that will be able to differentiate if you want to run this particular container using the WebAssembly runtime or you want to use the run C. So basically some configuration changes at the containerd.toml level that you can do, and where you can specify this particular runtime to be used, and that runtime can be the WebAssembly runtime. So I think that's pretty neat, and that opens up a lot of gates where you can use both the power of containers and WebAssembly hand in hand. It gives you the opportunity to use the same tooling, because education has been a major gap in the adoption. And now since you can use the same developer tooling that you have been learning for years, which is Docker and Kubernetes, you are able to now, with this particular feature set, use the same tooling to build your Docker containers, to build your WebAssembly modules as OCI artifacts, push that to Docker registry or OCI registry, and then run it as containers. Or when you come to Kubernetes as well, you can run it as standard deployments. So that's how it runs. Again, this is the same thing that I just said. So when the request comes to the CLI, it goes, gets the image, and then it tries to start the container, gets the container ID, Docker D passes it to container D passes it to the shim, and shim goes to the runtime, starts the container, gives back the container ID, creates the task, and then attaches the container and waits for that to exit. So that's the kind of process. I think it neatly explains the overall flow of how the Docker container works, and wherein the exactly you add a new shim over there, and you can play around with having multiple runtimes and targeting to different runtimes and run your Linux containers and WebAssembly modules. Just extending that part, WebAssembly and Kubernetes. Now again, I told you, the Docker coming into the picture, Run WASI coming into the picture, it opens up a lot of gates, and now you can use the same Kubernetes cluster to even orchestrate your WebAssembly workloads. So you can have a node where you can configure the WebAssembly runtime, and you can configure the containerd.toml file, and you can configure that, have a runtime class, and you should be able to follow the same flow, because in the end, kubelet passes all the request, tells your CRI, in CRI, if it's containerd, then it follows the same process. It goes to the Run WASI layer, and then the Wasm runtime, and then starts your container, and then it is running inside a pod. So I think that's pretty much the same that will be happening on Kubernetes. It actually happens, and we'll do a deep dive demo as well from scratch. So in Kubernetes, you can have different nodes. In one set of nodes, you can run your WebAssembly workloads. In another set of nodes, you can run your regular container type workloads. With the Run WASI release 0.9.0, you can actually run in a single pod a Linux container and a WebAssembly module. So I think that is also pretty dope. Just quickly trying to understand what needs to be done when we talk about WebAssembly in Kubernetes. So you have containerd Wasm shims. Let's say you have your Wasm edge spin shim, Wasm time spin, slides shim. You can have different set of shims. Then you have to you have to have the libraries and stuff for the different runtimes on specific locations. And then you need to change the containerd.toml file. In that, you need to actually specify the runtimes, if it's spin, if it's Wasm edge, and then you have to give the runtime type. It is also dependent on the Kubernetes distributions. Like if it's K3s, then it's CRI.containerd.runtime.spin. And if it's the whole regular kubeadm type of Kubernetes cluster, then it's standards plugin IO, containerd grpc v1 CRI, containerd runtime spin, and then you add the runtimes. After all of this is done, you restart your containerd, you create the runtime class, and then you label that node in a specific way so that when you create a Kubernetes workload, so you are able to provide a label selector to select and match and make sure that it goes to that particular node with a particular label where you have configured WebAssembly. In that way, you should be able to run the WebAssembly workloads inside Kubernetes. So just finishing up the theory part so that we can move on to the very amazing hands-on demo where we'll be building everything from scratch and all the way up to Kubernetes. So all the steps that I just explained for you to be able to run your WebAssembly workload or Kubernetes can be automated in a very easy way using an open source tool called Wasm. So Wasm is an operator to all the previous steps in an automated way. And we'll discuss more about this, obviously, when we do the demo. So now it's time for demo. And in the demo, we'll be creating a application, a Rust application from scratch, and then compile it to WebAssembly, and then try to run it, and then try to Dockerize it, try to run it via Docker, and then try to run it on a Kubernetes cluster. So let's do this end to end. For this application creation, there is a framework that we'll be using called Spin. So Spin is an open source developer tool for building and running serverless applications powered by WebAssembly. It's a framework that lets you easily create applications, and it has support for various languages. To install, it's pretty easy. You can just do brew tab fermion /tab and then brew install fermion /tab /spin. Since I'm on a Mac, so that's the one I'm using, but there are other install methods via the installer script as well. So that you can find on the docs on the developer.fermion.com/spin. And I have already installed Spin, and you can see that. So this is Spin at the time of recording 1.5.1 version. And you can see you can add a new component to an existing application. You can build the Spin application, publishing to the Fermion cloud so that they have their own cloud offering as well. Then deploy, package, and upload the application, Doctor to fix. And our point of interest lies in the new command, which is the scaffolding of a new application based on a template. And then you have other set of templates, registry, plugins, pretty cool plugins. You can create your own plugins as well and spin up to start the Spin application. So let's try to do that, and let's walk through and see what it says. So pick a template to start your application with. So it has various templates. So you have C, Go, Green, JS, PHP. Yeah, PHP. We'll do what the WebAssembly community loves the most, which is Rust. So let's create a Rust application. Let's name our application Wasm course. Description or Wasm course, the only course you need. And then we'll just leave it as it is. That's it. So we can go inside Wasm course, and you can see there are a few files which are already created. Now this is what we call skeleton. So the skeleton of your app is already ready. So it gives you a simple skeleton of your application, which on top you can build with your own business logic. So you can see you have a cargo.toml file. So you have a package, and it has a name, author, description, and then you have libraries. So create type, cd while lib, dependencies, and then spin SDK. So all these things are there. And then the interesting file is spin.toml file that actually defines how your application should be, what all components your application are using, when you build which command it will be building. So all these things are there. So Spin already uses components. So you can see the components which are there. And this will be the wasm course.wasm file that we would want to run. So what we'll do is we also have a source directory. So let's go into inside source directory. And you have a lib.rs. It's a simple Rust file with request response HTTP component. So it has a simple Spin HTTP component. And you can see it has a function called handle wasm course request response. And with a print, you can see the status and stuff. And in the body, it says hello Fermion. So let's change that to hello Wasm course. So we have done that. What we'll try to do is we'll do a spin build. So now it is building, and what we saw in the spin.toml file, it is using the same command, same using for Rust. So for Rust, we use cargo. It is also using the same command, cargo build -- target wasm32 WASI and release. So this will build the file and then put that into the target folder and create a specific .wasm file that you can run on any platform where you have the WebAssembly runtime installed. So the build is now complete. Now you can see that there is another folder, which is target. So let's go in target and let's go in wasm32 WASI, and we can see in the release, we have Wasm course.wasm. Now what we have to do in order to run this application, we can simply do spin up. As you can see, it is serving to localhost 3000. We can check that. In another window, we can do a curl to this and we can see hello Wasm course. So fantastic. This works. This works fantastically. And you can see the invocation happening over here. The next steps. Now we have created a spin application. We have actually run this application using spin itself. So, and we can deploy it to spin cloud as well, but we want to build a OCI artifact, which is a Docker container, and run it as a Docker container and ship it to the Docker registry so that we can move ahead with our Kubernetes goal as well. Before doing that, we can also try a very simple Rust file, use cargo, and then use one of the Wasm Edge runtimes to show you even before this, like how it looks like. So what I'll do is I'll go back one directory. I'll create a folder, Wasm cargo demo, and we'll do cd into that, Wasm cargo demo. We'll do a cargo new demo, and it has created a demo. It has created a source file, and it has a main.rs, hello world, and we'll do a hello from cube simplify. And what we'll do is we'll try to run the same command of cargo build and create a WebAssembly target for it. And we can try to run it as well, cargo run main.rs. So you can see cargo run main.rs runs hello from cube simplify. So this is pretty simple. Okay, this is pretty simple. This is the absolute base. Now we'll try to release it. The release is finished. So let's go back and we can see a target folder is there, and we can see again Wasm WASI 32 release, and then you can see a demo.wasm file over here. So we can use Wasm Edge run demo.wasm, and you can see hello from cube simplify as well. So like I said, you can simply create your own file, your own code. This is pretty simple code. The one that we created using spin was Rust HTTP application that you'll be able to serve. And here it's simple demo.wasm hello world file that you were able to compile using cargo itself and create a .wasm file and then run it using any WebAssembly runtime. In this particular case, we used Wasm Edge. Okay, now let's go back to our spin application. Now, in order to run the WebAssembly application using Docker, you need to have, I think, version greater than 4.21, and you need to enable the feature because it's still in beta and it needs the enablement. So what we'll do is we'll go to Docker, we'll go to the settings, and you need to enable the Docker extensions. And in the features and development, you need to enable the using containerd for pulling and storing images, because this is the place where you can see it has the ability to run Wasm container. So this is the features that you need to tick box and apply and restart so that you can run the WebAssembly containers using Docker. Now, before that, what we need to do is we need to build a Docker container, because right now what we have is a .wasm file. We don't actually have a Docker container. So first, let's try to edit the spin.toml file and see what we have. So before creating the Docker container, we need to add the dependency section in the spin.toml file where we specify the spin SDK and we specify the with bindgen Rust. So these two things have to be specified in the spin.toml file. Then we try to do a spin build. Spin build is done. Then we create a Docker file. In the Docker file, you can see we have from scratch, we are putting spin.toml file and we are copying the target Wasm course Wasm in the target Wasm 32 WASI release Wasm course.wasm, and the entry point is spin.toml. In order to build the image, we'll be using Docker buildx build platform. We specify WASI Wasm, and then we specify the registry name. In my case, it's Saiyam 911, and then the image name with the tag. So in order to run the Docker container, we should specify Docker run with the runtime container D span v1, platform WASI Wasm, and the port 3080. So that tells Docker to map spins 80 port inside the container to the local host 3000, and that's where you will be able to access it. So we can access it using like a different curl request, and we can see that localhost 3000 is working, and it says hello Wasm course. That's what we defined when we built the Docker image. We can actually do a Docker push of the image, Wasm course v1, and our image is pushed. So what we'll try to do now is we'll try it on a Kubernetes cluster. So how to do that? Let's do that, and we'll be doing it in a way that you can also try it on your own. So this is Killer Coda Kubernetes Playground. It is a 2-node cluster that you get. So you can see you have 2-node cluster. What we'll be trying to do first is configure what we discussed. Like you need to have a WebAssembly runtime libraries, and then you need to edit the container d.toml file, and then you need to restart container D. You need to have the shim properly blazed. You can avoid all those things by using kwasm.sh. That's what I also told you about. So kwasm is a Kubernetes operator that adds WebAssembly support to the Kubernetes nodes. It does by using the container image that contains binaries and configuration variables needed to run pure WebAssembly images. You can see a lot of stuff is already supported. So what we'll do is we'll go to the quick start. We'll do the Helm repo add of the operator. We will do the Helm install of the operator, and the kwasm operator is installed. So we'll do kubectl get thoughts -a, and we can see that the container is creating. Container is running. So let's clear the screen. And now we need to annotate the nodes. So basically any annotation that is added to a node, the operator will pick it up and configure that node to be able to run your WebAssembly workloads. So in this command, what we are trying to do is we are trying to annotate all the nodes so that it configures both or all the nodes inside the Kubernetes cluster and make it WebAssembly ready. It will be creating a job, so we can actually see pods -a. We'll be able to see the containers provisioning for control plane and for the node 1. So it is trying to configure both of those, and it has already completed for node 1. We can actually check it. So if I go to a new tab and I do ssh node 01, now I am in node 1. We can see the cat/etc container the config.toml, and when you scroll down you can see all the shims added. So you can see the kwasm container d shim spin. Obviously these were not there because it's Killer Coda plain environment that you get out of the box, but after installing kwasm and annotating the node, kwasm operator automatically configures everything for you and restart container D as well. So both of the control plane and node 01 are completed. So what next is to create the runtime class. So let's create the runtime class for spin, and we will do this. It's a runtime class, wasm time spin. So we'll create that runtime class. Runtime class is created. What we'll try to do now is create a deployment.yaml file. So this is the simple deployment file. So we are using the same Kubernetes concept. We use the same Docker concepts to package, push, run the WebAssembly workload. And now we are using the same Kubernetes toolchain, the same deployment file, where we are defining the kind deployment, giving all the label selector and stuff. Just we have added the runtime class that we just created. And in the containers, we added the image that we pushed for Wasm post. So let's run this particular file. kubectl apply, deploy. Now, when we do kubectl get pods, we can see that the pod is up and running. kubectl get pods -o will tell you the node where it is running. So it is running on the node 1. Now we'll try to port forward this. So kubectl port forward, deploy Wasm course 3080, And now what we can do is we can do in the new tab, curl 127.0.0.1 3000, and you can see hello Wasm course. So now we have successfully done a lot of demos. So let's try to sum it up. So we created a simple application using Rust, compiled it to target WebAssembly using Cargo, and then ran it using Wasm Edge. That was a first scenario. Second scenario was creating an application using Spin and running it using SpinUp. Third scenario was Dockerizing it and running it using Docker. Fourth scenario was creating a deployment manifest file and creating a Kubernetes cluster, configuring the Kubernetes cluster using KWasm so that it can run your WebAssembly workloads, and then applying that runtime class plus the deployment file, and then seeing it running on a Kubernetes cluster as well. So this shows with the power of existing tooling and the power of containerd run WASI shims that you are able to run your WebAssembly workloads using the same tool chain, same developer experience that you are used to in the cloud native ecosystem, using Docker and Kubernetes, making it OCI artifacts, pushing it to Docker registry, and then using it as regular Kubernetes objects like deployment and running it onto the Kubernetes clusters. So I think that's a very simple demo, and we'll dive into the more detailed and complex demos as well.
And now we'll talk about components in Wasm. And if you're around the Wasm ecosystem, you might have heard about components in Wasm, component model in Wasm. All of these are pretty trending topics, and you might have heard about them a lot. But in this video, we'll take an intuitive look at what components mean, how do you define a component, and then we'll talk about why do we even need component model. Up until now, we already saw what WASI is and how WASI opens a whole array of new possibilities. Now it might seem that, oh, but doesn't like WASI solve all the problems we had? We earlier said the problem was system calls, and WASI solved system calls for us. And now you're telling me that there's another problem. So natural question is, how did this another problem come into play? Why do I need to think about components? So first, this is what a Wasm module looks like. You have some kind of sandbox, you have the Wasm module running inside it, and you can roughly think of this as an object file in traditional compilation models. But unlike classical objects, WebAssembly modules can't describe system calls or reference any external symbols. They can only take numbers in and put numbers out, just like a traditional function. You do some kind of computation on it, and then you return something. So in this sense, Wasm is not a classical object, and it cannot like reference any external symbols at all. And that's about what Wasm does. With WASI, we want to have this ability to do interfaces. So we already talked about how Wasm module and WASI comes into play. But I want you to keep this in mind that the Wasm module is only limited to like these instructions. And right now WASI is only limited to these interfaces. And notice what's missing over here. What's missing over, if I just tell you some instruction and interfaces, is a better understanding of how processes are started. How does a process start? How does it interact with other processes? And when does it end? A better understanding of all of that is missing right now. And if I just see this, I don't know any of it. So that is indeed a problem with all that we just saw. So let's talk about what we want to do with components in Wasm. At this moment, let's not talk about components, but let's talk about what we actually want with the model we described. So in general, we don't want to talk about what goes in and what comes out of a function. We did that in previous videos. We instead want to talk about types, functions in themselves, methods, namespaces, and all of this makes sure how a function interacts or how processes interact with each other. So WebAssembly at its core is only able to exchange integers and floats. Anything more complicated than that has to be stuffed into the WebAssembly linear memory and then pulled out again, hoping that both sides of the exchange know how to talk to each other and can survive these iterative changes. If you make some change within the code that makes a WebAssembly module, and then use that WebAssembly module in some other place, because WebAssembly can just like exchange integers and floats. You need to make some changes on your own, and then hope the other people who are using your module know how to survive those changes, because you'll probably make a lot of changes how stuff is represented. So that seems to be a problem if we really want WebAssembly to be widely used, we definitely need some kind of interface description language. And if you know about interface description languages, they have been really common throughout with software. So we definitely need some kind of way to do IDLs or interface description languages. So now we talked about the problems and saw what the problems are. Let's see why component model can handle this. Exactly as we motivated, uh, component model has something called Wasm interface types. And just a sneak peek of what's coming next. It is exactly an interface description language, or mimics an interface description language. A Wasm component is simply a single typed object consisting of core Wasm modules plus corresponding with definitions, or the Wasm interface type definitions. Over here, what we can see, one of the components. So this is an example taken from the official component model GitHub repository. And what this shows is components can specify that they either export specific interfaces or require that other interfaces be exported. So here we have something saying use poll.poll.pollable. And you see that right now with the Wasm interface type definitions, we can get an idea of exactly what interfaces our Wasm module will export and what interfaces it requires to import, what are the types of it, and so on. So with that, we talked a bit about interface types, but there are also something called worlds, and this is more interesting than interface types. So there's a larger ecosystem of worlds. We talked about singular interfaces right now, but there is also a world. And the way this works is, this is just a standard syntax for writing a world. But the way a world works is, I have some world, and it says exactly what imports, what interfaces types it needs to import, what does it export, and so on. So we also take a better look at this. We'll have a demo, and we'll also see a code example where this comes into play with WASI, with some core system logic, and so on. So we also take a better look at this. But right now, you can just understand words as a better way to put together multiple interfaces and have this larger ecosystem. For better running code in one language and importing it in another, we need separately compiled components built from Wasm modules. So if you see what's happening over here, if we really want to run code in one language and import it in another, run some untrusted code, we need these components to be separately compiled and built from these Wasm modules. Component instances must fully encapsulate the linear memory to truly be able to run untrusted from one place and just use that code or function in some other place. This also includes potentially in the future garbage collector memory, which is kind of a problem because these are immutable copied values, opaque typed handles, and we have some uninstantiated modules or components if we do actually include garbage collector memory over here. Which is also why the component model right now assumes no global intercomponent garbage or cycle collector that is able to trace through cross-component cycles. And so you don't have essentially a process like a garbage collector or a cycle collector that is able to trace through all of these component cycles. So that is also a challenge when we talk about component instances being fully able to encapsulate their linear memories. So that's definitely a trade-off. And but right now, the reason why we need component instances to encapsulate their memories is to easily be able to run untrusted code and still maintain the use of sandbox model. Another thing to note with these components are destructors for component instances are deterministic. So what does this mean? We'll deterministically know when a component instance is going to be terminated, and each component instance has to terminate. So this is just something we also get with the component model, and each of your component is known to terminate at some time. So a genuine question that might pop up on your mind right now is, we talked about Wasm Module as this nice way to, or like a global IR of some sort, to be able to export code, run code from other sources into another sources. So a genuine question that might pop on your mind is, how different is this from the component model? And well, we talked about like what more the component model adds, but if you think about it, and if you're building an app just like this, you can have like each component of the app be a Wasm module of some sort, write them in different sources and then bring them together. The problem with doing something like this is we do not have like this process model being defined in the background. So interacting with each of these Wasm modules becomes really hard. If there's some kind of change with how the Wasm module represents things in memory, you'll have to potentially make that change on the host as well. And there's essentially like this one-off contract between the host machine and the Wasm module. So it becomes really hard to do it this way. On the other hand, if you do have a Wasm component doing all of these individual parts of your application, due to having like this general process model, it most certainly becomes a lot more easier to have all of these different parts of your applications as Wasm components under the hood. So that's essentially how you should use Wasm components. We already talked about how sharing memory between multiple component instances is a bit harder. So while designing such applications, you most certainly need to take care of those aspects. So the Wasm module or a Wasm component essentially has a separate compilation and deployment, but you could like most certainly have an adapter module be a component. A Wasm component also has fully explicit dependencies. We know what kind of stuff it will use, what kind of interfaces it exports, and so on. And well, a genuine question you might ask me is, this won't be true, and we won't be able to indeed use it like a black box if there is shared memory or there is something happening which is not from within version. And well, that is true, and that is indeed a trade-off we have to make sure that the Wasm sandbox model and the other benefits of Wasm which we talked about still remain. But in most cases, if you do not need memory to be shared across these processes, then Wasm components have a beautiful way of you being just be able to use it like a black box and reuse them. From a low level point of view, a component model is basically like an ABI, an application binary interface, much like ELF or the executable and linking format. So if you know all of these very early advances, you can draw a really nice analogy between Wasm components and things like ELF. If you don't know about like the executable analytic format, we'll also talk about what that kind of stuff means. It's very easy to see what this brings for Wasm and what other software had been bringing for Wasm earlier. Another thing we need to talk about is module linking. We haven't completely solved the problem yet. So module linking allows modules to truly be composed. So it allows some instances of any module and we can use these instances together. So we'll take a better look at this example in a while. But module linking essentially allows you to put together multiple instances of any module and use them together. So what we talked about right now is we already have like a layer of our core version, and we already know what this looks like with WASI as well. So now let's talk about how module linking comes into play and why we do need this in the component model. So note that interface types already copies all the linking concepts, and you can use it to link core modules, imports, or exports to adapter functions. And you can also use interface types to specify how core state is encapsulated. This you can think of like interface types are more like a feature proposal that in somehow extends like module linking. And like we talked about reference types that extended core Wasm earlier, that is exactly what interface types do for us. Extend this idea of module linking. And if we see hosts that do support module linking, but not interface types could also just be like an optional feature. But what this allows us to do is use some system functions and use other kinds of language APIs within our Wasm component. So we do indeed need interface types plus module linking to truly make the component model work. Earlier, we had things like Wasm link that allowed, which is essentially a WebAssembly module linker. It implemented the module linking proposal. I would most certainly direct the motivated reader to take a look at the Wasm link project for early developments in the Wasm space. And well, now all of this is encapsulated by our component model. So interface types is also serving this. The way component model truly brings all of this together is have some core, have some module linking, and then some interface types. So we should be able to use all of this together for component model to truly come together and get all the benefits of the component model. Here's the same example again. And if you take a look at this part of the code, we have some interface types. We have this adapter function. We tell what to export, what the parameters of it are. Looks very similar to the interface types we just discussed. So this is the part about interface types. We have the part about module linking as well. We have an instance of code saying import libc. We have a module libc, and then we instantiate libc. The part about importing libc malloc and using the function export run, which is function export run. Well, all of that is actually core, but we have these instances of code, which is import libc and instantiate libc. And all of that is due to the power of module linking, which we just talked about. So let's talk about Wasm interface types. And until now, we have briefly been talking about Wasm interface types and intuitively motivating how they can be used. But WID packages can contain world definitions at the top level in addition to interface definitions. So we already saw how interfaces and worlds are nicely come together. And you can think of world as a complete description of both imports and exports of a component. A world can be thought of as an equivalent of a component type in the component model. As promised earlier, here's an example of what a world looks like. So remember I showed you the framework for what a world should look like? Well, let's use the same framework here. So worlds essentially describe like a concrete component and are the basis of any bindings you'll generate later. So you can use a guest language. When you actually run this in a guest language, they'll use a world to determine what functions are imported, what those functions are named, and what functions are exported. So we can have like any number of imports and exports, and each of these imports exports can either be a function or an interface. Essentially, if you think about it yourself, it's just like this nice way to stitch interfaces, because we do indeed want it like a nice way to bring it all together. We talked a lot about like this exchange, right? Between what functions are imported, names of the function, and so on. We didn't really talk about how the exchange will actually happen within the component model. Now, that is indeed something we don't care about at all. We don't care about the details of how the guest and host agree to exchange those strings. But tools like WidBindGen, which is actually a really popular tool, will generate the functions needed to do that kind of marshalling for us. So right now we are just concerned with understanding how these interfaces and functions are exported or imported, and we'll have other tools like WidBindGen, which we, for the scope of this video, we don't go into, but those tools will actually handle the exchange for us. So we talked about all of these aspects, and all of this is very well extendable to WASI as well. In your mind, you should have already done this since we talked about WASI earlier. So essentially what WASI does is, if you have like this WASI layer, we already talked about the component model spec. We talked about the different things that the component model has. But WASI wants to define its interfaces in terms of interface types. So, and what that means is, you see the WASI spec layer over here. The WASI spec would essentially have to depend on the component model spec, because its interfaces will be defined in terms of these interface types. As we already talked about WASI earlier, you already saw that the use of WASI isn't restricted to components. And tools which are producing or consuming core modules today would still be able to do that without the component model. And we actually saw examples of this in earlier videos. And also, when you're using a WASI from a core module, WASI basically looks like what it does today for you. The component model factors out what WASI would otherwise duplicate in its own interface description language. So we have like a single place to describe all of this now. And of course, when using WebAssembly system interface from a component, you get some benefits, which are component instances, encapsulate their memory and handle tables themselves. And components can essentially also virtualize WASI without causing a lot of problems, or a problem we generally call caller's memory in traditional software. Overall, what this allows you to do is, eventually you can avoid deserialization with adapter functions at all. So it most certainly, using WASI with the component model makes stuff a lot easier for you as someone writing these Wasm modules and making them run. We'll most certainly see examples of this, but right now all we did is try to understand the need of component model, the problems component model solves, why what essentially look like a nice way to just run things in Wasm, it still had some limitations, which we solved with the component model and module linking. So with that, we come to the end of this video. And next up, we'll also take a look at how to implement all of this. And we'll see a few examples of doing that. So now to put all of this together, we'll take a look at this demo. And we'll do exactly what I show here. So we already talked about it, which is the Wasm interface type. So first what we'll do is we have this dynamic library, or as you may know it, stdy lib in Rust. So in the dynamic library, we'll use WebAssembly Rust to create a component we want. So this will allow us to use the Wasm interface type definition and also create a component for us. So then we right now are at this stage where we have a component, and we already created the component from some Wasm module I had, from some Wasm interface type I had, just so I could make use of functions and words and everything. Okay, so now I have a component definition, and all of this is done beforehand. None of this is pretty much used while running some untrusted code. And now what I want to do is I have this runner. Runner is a completely separate project. And let's say the goal of the runner is just to use some untrusted code, some untrusted WebAssembly code from some other language. I mean, for the example, we'll just make it consistent and have all of this in Rust. But this could be like any language. But more about that later. So we have the runner. What we can do is we can also create a component instance. So one of the ways you can create a component instance is use with bindgen host and use a component encoder, which allows you to read the component and just encode it with your Wasm module. So you could most certainly do that, but that probably doesn't sound the best thing to do. You would always need to have Wasm module as well as with and then do this encoding while runtime. So probably doesn't make the most sense to do that. What you could do, what you might have guessed you could do, is you can create the component instance definition beforehand. So you can use the component encoder, go from the Wasm module and also encode the component. And then at runtime, you can just use this component instance or run this component instance or make an instance out of whatever component definition we created beforehand using a Wasm runtime. And this part you could most certainly do in any languages. So you could probably have your Wasm module, dynamic library, and all of this done in some language, run the component instance in an entirely different language, because then we just need to run the component definition and make a component instance out of it, which is pretty easy to do with the Wasm runtime, right? So this is the overview of the demo we'll be seeing. And I try to do exactly the same thing. So let's get on with it. First, what I do is I have some width, and first I start seeing width bindgen. If you remember the diagram, I start seeing width bindgen as one of the first lines in my code. So what we are trying to do is I'm just using a very popular crate on Rust, and that allows me to render some markdown. So how do you do that? You want to take a string, which is something you wrote in markdown, which is a string, and you want to go to HTML. Right now, we'll just say HTML is a string as well. Okay, so that is what we want to do. And the implementation for this is pretty easy. I just have this render function that goes from a string to string. I don't write the markdown renderer myself. I don't want to do that right now. I just use a simple Rust crate. Now, this line 12 seems a bit familiar. And I have a struct here. I have an implementation here. So what's happening? First, let's see line 4. We have width bindgen over here. The width bindgen tells me I want to use this width, and I have some world, and it also tells me what it exports. So let's find the width first and take a look at this width. At this stage, you already know what each of these things mean because you went through the slides earlier. So we have this renderer world. We have this interface which is being exported called markdown, and that has a render function inside it. So in lib.rs, we create this struct called myMarkdown, and this will implement the markdown struct we had in our width. If you remember, I also had the render function in which it was exporting, and this is exactly that render function. I'm implementing that render function from the width right now. With this, I have a width and I'm doing all these things. So first what we want to do is we want to compile this, make our Wasm module. So let's do that. It's pretty easy to compile cargo projects. So what we can do is just do cargo build. So let's do that. So we compile this and let's check out what our target has for us. So we have the version 32 unknown minus unknown, which is the target I specified. And I also have some cache.wasm. So now we have this host and let's take a look at the main.rs. So the first thing we want to do is use some component encoder and encode our bit into the Wasm module we just created. So this could also be a simple command. So you can also do it with Wasm tools. Ideally, you would actually want to do it with Wasm tools. So you just have this command called Wasm tools component new, and using that you can just create like a component definition. So there's no need to do this in runtime, as we were talking about earlier. I just want to show you how this looks like. So I have my Wasm module. This is where my Wasm module resides. The Wasm module we just created. So what I'll do is I'll use the component encoder and I'll just encode the bit definitions and the other component definitions we had. And this will allow us to create a new component definition. So now that I do this, what do I want to do? Now I have this component definition. I actually want to run it with a Wasm runtime. So let's do that. So I'll be running this in Wasm time. And for that, what I'll do is I first have this bindgen. And what this bindgen does is it was just taking the width we had earlier and using this width for any function or interface definitions. So running this now gets pretty simple and we can actually do it just using Wasm time. So that's what I'll do. So Wasm time has the ability to specify that you want to create a new component instance, which you aren't doing at this in the highlighted line where Wasm time just allows you to take this component. So that's what we do. And then we have this instantiate. So what this does is actually creates an instance, the component we had. So this will also use the world we generated earlier in the .bit files. So that's what we have over here. Now I can just use the functions that I was exporting. So let's take a look at our bit again. And I see that it's exporting this function called render, which I actually want to use. This function is no longer an interface. We already implemented this earlier. So what I now do is I use this exported render function and I call it with some markdown. And then we just see what this looks like. So what we'll do is we'll run this host code. So for this, I'll not use cargo build. I'll just do a cargo run. I want to run this Rust code. I don't want to create a module out of it, just like we talked about in the figure earlier. This is actually what would happen when using the Wasm module, the Wasm components, creating a component instance out of it. So let's actually do that. And it should take a while to compile this. With that, we see it actually worked. And it does give me some string, and this is indeed the correct representation of the markdown we had. But what we really wanted to see is all of this happening under the hood. So we actually created a component, we had some Wasm module, we used the Wasm interface types, we created a component instance and then ran it using the Wasm runtime. So all of this is what's happening under the hood. So with that, we took a look at the component model, which is a pretty interesting idea with WebAssembly. And maybe now you also understand why component model is useful in the first place and why we needed a component model and what basic need was it solving. So I hope you understand those aspects about component model. And we also saw how they use component model in WebAssembly and the role interface types, the role linker, and the role all of these components and all of these subcomponents of the component model play and how they all interact with each other. And we also saw how you can use component model for your own applications. And mainly we saw how this could extend to using WebAssembly binaries, but not having to worry about changes percolating on both sides. So it being really hard to track changes when you make a change in Wasm binary and some function changes, and then you need to make changes in your host as well. So we mainly saw how this was a nice solution to all of those problems and solved our really fundamental problem or something we didn't have earlier in WebAssembly. So that's about the component model. And I'd most certainly urge you to also take a look at particularly how this works in the context of WASI, as well as how you would extend this to, let's say, you have some new code libraries. How would you add support for them? So I'd most certainly invite you to take a look at these other aspects which you won't talk about in the course. So earlier we took a look at the component model, and the component model solved a lot of awesome problems for us. Now let's take a look at using Spin to create and the composition of components. So Spin allows you to do this very easily, and you might already know about Spin through the earlier videos. So let's take a very simple example of making a Spin component and running it. So this is a very simple Spin HTTP component, and all this does is just serves at the path/hello, quite literally just write something. So this is a very, very simple Spin HTTP component. And let's try running this. Especially with Spin V2, you have the ability to create and use these components, and it's also very easy with Spin to create component compositions, which I think is really interesting. So first I can do a cargo build. So let's do a cargo build. I can pass in minus target was 32 minus WASI, and I'll also pass the release flag. Now what we can very simply do is just run spin up as they had seen earlier. So let's try doing that, and at least for this very simple example, well, pretty much all we need to get the component serving. So the path was /hello. So let's try going to /hello, and there it is. Just prints it out as we expected. Nothing really complex with it. This is how you can very simply use spin components. This, for instance, was one of the very simple pre-built components with spin, and you can use multiple such components. Yeah, that's also how you use a spin to create and use components.
So at times we do require to store the data. When you're using Spin, you can actually use a key value store. And in this particular example, we'll go through the key value store example. So first is creating a new application. So we do Spin new, and we'll create a HTTP Rust. We'll name the application as pizza. So what we actually want is we want to add orders. So we'll be adding the pizza orders, we'll be getting it and we'll be deleting it, and we'll try to see. So we'll try to have a state in the key value store, and at the runtime of the application, we'll add, remove, and get from the API. That's what Spin does. It automatically creates, we have seen that the cargo.toml file, it automatically creates the spin.toml file and the base source file. Now what we have to do is inside the component build the key value store over here. So let's edit the spin.toml file and go in the component spin pizza. This now the default key value store is SQLite, so that will be used. Now what we'll do is we'll write a simple Rust code. So here's the simple Rust code using the Spin SDK, the latest one, and it has a function handle pizza. So what it is doing, the main thing you have to see is post. So on the post method, it should be added. So we get store.set. So, and what is store? Store is the open.default. So this is the code. And you can see we have imported key value as store, and you can see we are opening it over here, and inside that when we do post, adding that, getting the details from store.get, and for deleting it's store.delete. So those are just the three methods. Now what we'll do, we'll simply do spin build, and it will start building it, and actually what it is doing, it's building using the regular cargo build -f target. So once it's built, what we can do is we can do spin up. So once this is up and running, we'll go to a new tab and we'll try some curl commands. So let's try out the get from order 1. Like we haven't placed any order there yet, so it should be a 404, which actually it is. So it's a 404 on the order 1. Let's try to add something on this order. We'll use the post and we'll add pizza, pepperoni, extra cheese for order 1. It says 201 created. Now what we do, will again try to get the order, and we can see we have successfully received the order, and we see pizza pepperoni with extra cheese. We can place order 2 with no cheese, and we can check for order 2, and we can see it's no cheese. We can delete the order to, and it's deleted. If we try to get it again, it will give the error that it's 404 because we have removed the order. So that was a quick demo on the KV store, how do you spin KV store, and how you can have some state. You can read from the state, write to a state, get it, and delete from that as well. And the default one we have used over here is SQLite.
So now we'll be talking about inferencing machine learning models with WebAssembly, which has become increasingly popular today due to the various benefits we talked about. There have been quite a lot of approaches about doing this in WebAssembly. There have been approaches where you compile parts of TensorFlow code, parts of PyTorch code base completely into WebAssembly. And there have been multiple different kinds of such approaches in the past. For this video, given all that we have talked about in context of WebAssembly, we'll be talking about WASI, which is a modern way of the machine learning inference with Wasm. And this should be particularly straightforward to understand based on what we have been talking about. So a lot of the challenges that WebAssembly solves are very useful for such kinds of machine learning runtimes. So you must certainly have the WebAssembly modules just being created as you do create it. You have the Wasm runtime, and then just like WebAssembly system interface, you have WASI with another set of system calls that are required to, for example, use the GPU or use other machine learning specific operations. And then you have machine learning backend under the hood, which powers all this. And we talked about how WebAssembly uses the linker to support multiple such backends as well. That's also how this works. And WASI supports multiple backends, TensorFlow, PyTorch, OpenVINA, and so on. So under the hood, you still have those APIs. You can use them within your WebAssembly modules. So that's a quick understanding of how WASI works. Conceptually, it's pretty straightforward to understand given what we have been talking about. Let's take a look at a very simple example. So the way we'll do this is I have an application here, some simple Rust inference code. So we can take a look at this. And we use multiple functions from WASI. So for example, at least for this example, this is a very small model. So I run it entirely on CPU. I use the PyTorch backend, and this piece of code allows me to load in the model itself. And then WASI also has APIs for us to do inferencing, get inference labels, which we then show. So WASI simply has APIs to do these kind of aspects. And the way it does this is simply uses the PyTorch backend under the hood. So you have this WASI as a layer of APIs for the PyTorch backend that you can use in WebAssembly, following what we have been talking about previously. So that's what WASI does. Over here, we say we want one batch size inputs and 224 images. Yeah, we want this kind of VGR images. So that's what we'll be doing. And I just have standard boilerplate code for such kind of simple image classification models. So we're most certainly interested in WASI, but we aren't very much interested, at least right now, about how this model is exactly built. This one is a MobileNet model, but you could most certainly do this with all kinds of models. You also have ways to do this for LLMs, and you have inbuilt APIs to do this for LLMs as well. So now we can take a look at running this very simple code example. I can start off with just running a cargo build. So I can do cargo build minus target, wasn't 32 minus WASI, minus release. So now what we can do is use Wasm to run this piece of code. So let's first see what this generates for us. So this should be Wasm 32 minus WASI / release, Wasm edge minus WASI and then example mobile net image. Minus name model that wasn't. So we can take a look at this, and we do have a WebAssembly module generated over here. So this is what we can use. And you can also use the Wasm utility to AOD compile this if you want to. Well, this printed out quite a bit of it, but you can simply use Wasm to compile this down to AOT code as well. So that is about the Rust inference code that we had. And what I also have is an example for us to take a look at. We can just see that we do have an input image, and I also have a preprocessed image in the format that we require, the BGR channel format that PyTorch requires. at 224 by 224, resize to that size. So I already have that image over here. Now what we can do is run this as we would for any other WebAssembly module. So now let's try to inference from the simple Rust example and our WebAssembly module that we had. So we can inference from this as if with any other WebAssembly module. So we can first pass minus minus there to give it the paths that the WebAssembly sandbox has access to, and then pass in the model path that we have. I have two models over here, a name model and a standard model. So you can also use name model features with WASI and Wasm Edge, and that is quite straightforward to understand. As of right now, let's just write an inference with this. Next up, let's give the part to the model weights, which I have just over here. And then I have this example image. This has started inference, and this will soon print out an inference it does. However, this is mainly to show that it has been able to read the image, resize the image, convert it to the batch size we want, normalize the image, then create the graph, create the WASI and an execution context, which we shared earlier, and then actually do the inference. And you could most certainly try this out for larger models yourself as well.
Now, let's talk about Wasm observability. Before we get into the WebAssembly observability, it's important to understand the basics of what observability is. So observability is just getting more information about the application. There are like 3 layers into it, which are like metrics, logs, and traces. So metrics meaning any data that can be aggregated and can be counted as a metric. With more and more systems, application, this becomes a very important metric, like very important piece, as it tells you how the application is performing over time and also how the system is performing. People who are familiar with the cloud native and Kubernetes ecosystem, you might have heard of a tool called Prometheus. So simple example would be Prometheus scraping the metrics from different targets at regular intervals. Then comes the tracing. This is important when we talk about the microservices architecture, as it gives the insight into the application running inside any platform, whether it's like a Kubernetes or something. Then capturing the traces of the request and determining what is happening throughout the request makes it easier to find the issues, easier to find the latencies, which particular trace of the application is actually causing the problem when a problem actually occurs. Again, talking about the cloud native folks, you might be familiar with the tool called Jaeger. So Jaeger is a popular tool in this particular space. Coming to the final piece, which is the logs. And I think most of us who have written applications, you have used logs. All of us have used the log analysis for debugging at some point, when we have written the application to get to the root cause of the problem. And when we talk about complex system, microservices, any type of application, there are a lot of components, each components emitting different logs. The structured logging becomes important. And the tools, again, you can compare the logging tools such as Elastic, Loki, and some of the other tooling. So these are the 3 key things when we discuss about observability. So you have metrics, logs, and traces. Now these metrics, logs, and traces are stored into a database, like a time series database or whatever database that is there. And then there is a query layer. So as a user, as me, so what I want to do is I want to use that single query layer and get the meaningful insights from my application so that I can debug it faster. You also might have heard about the complete cycle of observability, which is called like observe, orient, decide, and act. So as an SRE or whatever that you are in the team, or as a DevOps engineer, you are continuously observing the system. So I'll give you an example. For example, an SRE starts their day. So usually when SRE starts their day, they always go through some of the dashboards, some of the tooling, and check the alerts which are there, try to find what is happening. So that is the orient, the root cause analysis, and then discuss and decide how to fix them, and then actually do the changes. Either it's a short-term fix, if it's a one-time bug, or if it's a long-time occurring bug, and try to do the push the code changes to make the longer-term fix for that. Overall, observability gives you better understanding of the system and the application. It helps you with better troubleshooting and also the dashboards for the performance and health of the application and systems. And now when we talk about Kubernetes, obviously Kubernetes is a complex system, so it also gives the health of the system. That's why I said dashboard for performance and health of applications and system. Here we are going to talk about obviously WebAssembly observability, why it is difficult, and how you can do. But before that, again, let's try to understand observability with the help of another example so that our concepts become clear from here. So there is a user. A user has written an application. Now, that particular application is deployed onto a system. That system can be any system, a virtual machine, Kubernetes cluster, and it has a URL. Now, a lot of users are accessing that URL. So that URL is your application. That is the user-facing application. That is the application that you have given to your users for your product. And users are accessing your application. There are hundreds of thousands of users who are accessing your application. Now, there can be days when things fail, and you need to find out what failed, when it failed, what is the slowness all about, which part is slow, which part of your application page is slow, how many 500 errors, how many 400 errors, is there any DDoS attack? So there has to be an observability system in place to get answers for all these questions. Now let's come to challenges in WebAssembly observability. Now whenever the application is deployed, what happens? Usually you will have the application, you will have an agent that will be capturing all the metrics from the application. Agent is deployed on the host. If in Kubernetes ecosystem, it can be deployed as a daemon set. It also can be deployed as a sidecar so that it captures and then it gives to a centralized agent, and then that forwards all the metrics in chunks to a big system like, New Relic, Datadog, OpenTelemetry, and stuff like that. But in WebAssembly, modules do not know about the host. That is one of the biggest challenges. Like WebAssembly modules do not know about the host, so they don't know where to interact and where to send the metrics. So the thing is, you actually can open some of the connections, but you don't want to keep the connections open for a longer period of time, because as metrics, you need timestamps. Now, whenever the metrics are sent, you need the exact timestamp, so the connections have to be open throughout. So you need access to system clock, and that too continuously. WebAssembly module should be able to make IPC calls as and when required. WebAssembly also do not have access to the system. You already know now, by now you know what WebAssembly is. Like it is, independent and independent of the OS. It doesn't have any knowledge about the operating system and host system. So that is the reason the observability thing in the WebAssembly ecosystem becomes difficult. Now what we'll do is we'll discuss two areas and show how we can achieve some sort of observability. The first one will be WASI logging. So WASI logging is a simple logging API, and it can be used as the standard error like the stderr destination, and it has different input levels. So you might have seen log and then level. So there are different levels like trace, debug, info, warn, error, critical. Then there is a context, like whether it's a log, whether it's a info, and then there is a context. Context can be string, like whether it's stderr, err, and then comes the message, the actual message, so that you know what exactly the message is when that particular log occurs. So what we'll do is we'll try to see it with the example. For the demo purpose, what we'll use is I have cloned the repository of Wasm Edge, the Wasm Edge itself. And then there is this examples plugin and WASI logging. So I am right now inside the WASI logging directory. So after the git clone and going inside the WASI logging directory, what we can see is cat src main.rs. It just has the use WASI logging example and WASI logging demo. So what we'll do is we'll see the lib, and inside that we can see different log levels. So that's what I was telling about. First, we have the level. So we have info, then we can have a string, and then that's again a string. So info, context, and message, three things are there. And these are the 6 level, right? Trace, debug, info, warn, error, critical, and then the context, and then the trace level message, whatever the level of message it is. And then some of the function calls over here. And here we are passing the context. So you can see we are demo template passing stderr. So it goes here stderr, what becomes in stderr. So we'll get to see all these things. So in order to run this demo, a few things. First, you should be having Rust installed. You should be having Wasm Edge installed. You should be having a plugin installed as well. So you should be having Wasm Edge plugin, WASI logging for the particular environment that you're running, where you can download this, or you can directly build it when you have the cloned the repository, or you can directly go to the releases page and download from a particular release the WASI logging plugin and put that in the plugin directory. So these things you have to do. After this, what you have to do is build. So we'll do cargo build, target, Wasm 32 WASI. Once finished, we will try to run it. And we can see we have directly run the Wasm Edge. And for the first level, we can see the info level logs. We can see 3 kinds of messages. We can see the trace. We can see debug. We can see different colors for that. We can see critical. And then we can see different context chasing. So demo 1, we can see std out messages. So this can be direct std out messages. Level 2, demo 2 is the std out message without the context, where the context was empty. And the third one is the stdr err, where the context is error. So we can provide different level of context with different levels of trace, debug, info, warning, error, critical that have different color coding as well. So this is one way in WebAssembly using WASI logging that you can have logs. Moving next is something by Dylipso called Observe SDK. What happens here is you have the WebAssembly code. You now instrument that code using something called Observe API. Now that Observe, everything is open source. So Observe SDK and Observe API, both are open source projects. And you can use Observe API using manual instrumentation or auto instrumentation. And then you will be having the Observe SDK adapter that will be sending data to OpenTelemetry, Datadog, and there are different types of adapters. So let's look at these adapters first, like look at their documentation first, and then we'll go through one of the examples as well. So this is the Dylipso Observe SDK GitHub repository. You can see Observe API is over here, and then let's go through it. Again, it provides the SDK for WebAssembly for continuous monitoring, and it has the supported telemetry to Honeycomb, Lightstep, Datadog, and OpenTelemetry. So it has different adapters in different languages. We'll be using one in Go and also in OpenTelemetry. The example here is of OpenTelemetry. We'll try to use a bit OpenTelemetry std out, and then instrumentation. So one is automatic instrumentation. So automatic instrumentation usage is like you have the code and then you put the API key, and API key you can easily generate here. So click here to automatically instrument, and you should be able to get a generate key, and using that key you should be able to automatically instrument the code. There is a manual process as well, where you have the metric, log, span enter, span exit, and span tags. So this also is there. Right now it is there in Rust and C. So let's try to understand how the instrumentation would look like. So the instrumentation would look something like this, where you have hash instrument and you have metric. So you use the Observe API. So you have the instrument, log, metric, span, enter, span, exit, span tags. Now here what we are trying to do is log something. It is passed, hello world 1 is passed here. And then it is just metrics, and the metrics format is stats t and hello world, and the log is level, where you can provide warning, and then you can provide this same string message over here. That's what this particular thing does. And you can also use span tags over here. So what we'll use is we'll try to use one of the examples of count vowels. So this is the count vowels. If you see, this is the code, this is the Rust code of counting the vowels. So you have the constant of vowels, you pass it, and it reads the characters, matches, if anything is there, it contains, and then it simply prints the count number of vowels. What we are going to do is we'll be using its auto-instrumented WebAssembly module, and then try to run it. But the key part here would be the adapter. Now this is the auto instrumentation. Auto instrumentation is something which is there. Now we'll be using the adapter. The adapter what we'll be using is the OpenTelemetry adapter. So let's try to look at that. We'll be using Killer Coda Ubuntu Playground. Now one thing we have to do over here is change this to, like, it has Go version as 118. So we'll change this to 120. So let's do that first. So I've just fast forwarded all the steps required to have the Go 1.20, and we can see Go 1.20 is there. Now what we'll do is we'll also install WASI. So WASI is one of the WebAssembly runtimes. So we'll have WASI installed over here. We'll also get the auto instrumented code because we need that. So let's get the auto instrumented code. And what we are going to do is we'll do go mod init demo. We'll create a main.go file, and in the main.go file, now this is the adapter code. So I have tried here to keep things simple. You can also check the OpenTelemetry's example where you can specify the OpenTelemetry and the agent, and you can use any local Zepkin or whatever agent is there to get the metrics out of that. But here it is just the std out. So instead of OpenTelemetry, we are using the OTel std out, which is there. And here it is the adapter. So this is the new OTel adapter. This is the start command for that. This is just simple error. This is the WASI runtime. So we need that. And after that, it is the observe SDK adapter applied to the WASI runtime. Then the WASI configuration, and then instantiating the Wasm module. So this is the instantiation of the WebAssembly module, which is there. And then it adds some additional metadata, and it should give us some OpenTelemetry output. So that's what it is. Let's try to run it. We still have some dependencies that we need to go get. So let's go get all these. And now we are running it, and we should be able to see some OpenTelemetry std out data from the auto instrumented code using observe API and observe the main.go. Here we have used the OpenObserve adapter for OTel std out, and you can see we have all the std out over here, the data, and this is something which is not very much readable. But if you see, there are like resource spans, and you can see all the trace IDs, and you can see values, the function calls, the span IDs are over here. And if you pass it as OpenTelemetry, or if you pass it to a particular agent, then you should be able to see in a fancy way, much more organized way, and then you can visualize according to yourself. So yes, observability in WebAssembly is hard. And also the OpenObserve, like the Dalebso team is working towards getting it accepted as WASI observe definition. It is hard, but companies like Dalebso are working towards making it efficient. So which is cool. And you have WASI logging, so you still have a few options, and I wanted to cover that in this particular course so that you know that what all is there when we talk about observability in WebAssembly, and how you can actually instrument your code automatically or manual or using WASI logging. So that's it for Wasm observability.
Hello, and now we come to the end of this course. Throughout the course, we used various demos and examples which are available under the Wasm course repository. We have placed a link to in the description of this video. And hopefully this course has given you enough WebAssembly knowledge to start building cool stuff with WebAssembly. But one of the other things that we have tried to do with this course is, instead of going through every nitty-gritty and writing every line of code in the course ourselves for everything, if we have tried to give you enough knowledge to start building stuff with WebAssembly and also start exploring stuff with WebAssembly yourself. So let's say tomorrow there's some new feature in WebAssembly. You'd be able to explore it by yourself without having to go through any course. Let's say you want to build the new feature in WebAssembly yourself tomorrow. You'll be able to do that without having someone guide you line by line. And that was one of the main motives of this video series, to have you be equipped to build cool stuff as well as be all ready to explore stuff in WebAssembly yourself. So let's take a quick look at what we learned in this course. So we started off with a history of WebAssembly, why WebAssembly came into play, and why was it even a problem that was worth solving. We then took a look at how WebAssembly works. And at that time, I bet a lot of you might be thinking how WebAssembly might be different from Java Virtual Machine and those kinds of deployment formats. So we also talked about that. We then talked about WebAssembly was originally built for JavaScript. So we also talked about how it worked with JavaScript and now how it's working outside the browser as well. We then talked about different Wasm features, We talked about the very vast and very interesting CNCF Wasm landscape, which is multiple tools and tooling that have been developed around Wasm, which is actually pretty cool because for a lot of time, there was a big problem about enough tooling around Wasm. There wasn't enough developer tooling around Wasm. So that was nice to see. We then took a look at some of the specifics of Wasm. We took a look at how memory is being managed in Wasm, how linear memory helps solve some of the problems. Embedded is also not without any challenges, so we took a look at those challenges. We then talked about Wasm Sandboxing and how Wasm is secure by nature, how some of the promises of Wasm come into play. We then talked about what exactly is a WebAssembly module and how do you, if you wanted to, how could you handwrite a WebAssembly module? We also talked about that. We then talked about some of the tool chains around Wasm and how you could compile languages to WebAssembly modules, how you could run those WebAssembly modules in other languages. So we talked about these kind of tool chains. We also talked about how runtimes run these WebAssembly modules and exactly what goes on into running these. We then talked about one of the focuses of this course about Wasm on the browser, where we mainly talked about this to set up for how WebAssembly is not only limited to the browser, even though it was built for the browser. So we talked about WASI WebAssembly system interface, we talked about component model, and we also talked about different modifications to WASI that have come in recently. We talked about WASIX, we talked about WASI Preview 2, we talked about how you can start using them, and then we also talked a bit about what different kinds of use cases could you use Wasm on the server for. We then talked a bit about networking and WebAssembly. We talked about the WASI networking proposal, which is really important to make WebAssembly well-rounded and suitable for all kinds of server applications. Very related to that, we also talked a bit about Spin, which is a popular framework to do this kind of stuff. We then talked about the component model in detail. What actually is a component and how do you build with the component model to allow for building richer applications with WebAssembly. We then talked about how you can use WebAssembly in Kubernetes clusters and have Kubernetes do all the orchestration for you, which is pretty popular. And there are quite a few cloud providers, popular ones, including Azure, which already support right out of the box doing this kind of stuff. But we showed you exactly how this kind of stuff works under the hood. We then talked about how you could create an end-to-end full application with WebAssembly, WASI, running it on the server side, having some form of PV store, and doing some form of networking as well. We then talked about and showed you a few interesting demos, how you could leverage machine learning inferencing with Wasm. We particularly take a look at how Wasm can support different kinds of backends and popular frameworks from other languages. We specifically took a look at PyTorch examples and how Wasm can support those kind of different backends. We then took a look at observability and how you can get some observability for your Wasm modules. And that was all that we covered in this course. And that was quite a bit of it. But most certainly this course is not exhaustive. So I'd urge you to take a look at any of the videos again if you need to. That is quite a bit of content. Now let's talk a bit about some of the future prospects in WebAssembly.
Yeah, so that was a nice roundup of what we covered in this particular course. So as Rishit mentioned, this course enables you to start building stuff. So you now should have all the knowledge with all the concepts, with all the terminology, and quite a handful of demos as well that you can go check out, do on your own different systems, and then build on top of it. And if you happen to build some cool stuff, do tag us on the social so that we can celebrate together what you learned and what the wins are. Coming to 2024, what's in the bag for WebAssembly, in my opinion, definitely, like, I am a cloud native and Kubernetes fan, so I always start from that angle first. So that would be the WASI integration, and the WASI integration getting more matured, and we'll soon start seeing multiple cloud providers to provide the native WebAssembly nodes as an option for the Kubernetes offering. So what that means is you create a Kubernetes cluster, so you will be able to easily create a different node pool which has WebAssembly pre-configured, and you can just have a node selector or node name or whatever criteria that you want to target that particular WebAssembly workload to the WebAssembly configured node. So that It enables the same developer experience that you have learned for like quite a few years, and you can use the same DevX to create and run your WebAssembly workloads. Coming to the component model, which everyone was excited in 2023, we have seen a lot of implementations. We have seen in Spin 2.0 how component model has matured, and we keep on seeing it getting matured and getting more widely adopted. Simply means you'll be able to use the library that you love in one language to be imported and used in another language, reducing the duplicacy, improving the efficiency and the reusability of components. Then WASI Preview 2, we also will see the increment networking support, more number of system calls in that. So I think that will also get matured, and then all the APIs being implemented within the specific runtimes. We'll also see more proposals, I think, in the WebAssembly observability space, and also more implementation. So we'll see more and more innovation around the observability and the debugging space, because that is interesting. That is a bit tough when we talk about WebAssembly, because as explained in the course as well, it is, WebAssembly, because of its isolated and secure sandboxing, doesn't know about the host, can't do, the syscalls natively, and its capability based model makes it limited in terms of how we can observe the WebAssembly model and debug that. There are still tooling which we have already shown, and then I think there will be more interesting tooling being developed or matured in 2024. Coming to AI, we have seen in the second half of the year mainly AI inferencing matured in the WebAssembly space. So we have seen more and more of AI inferencing being done as WebAssembly. So we'll see even more growth in that. Growth meaning more models will be supported by the runtimes, specifications getting more stronger for supporting various AI use cases. So that will happen. One of the features, garbage collector, will continue to get improved as well. So I think those are some of the key areas that will see more enhancements in 2024. On the adoptability side of things, I think this year can prove to be one of the years where WebAssembly adoption becomes like very, very common. Why we see this? So we have seen different conferences like WasmCon, WasmIO, Cloud Native Wasm Day. So we have seen all these. And if you see the pattern, if you see the type of talks that are being delivered, people are actually bringing more and more use case based talk, which shows people are actually using, implementing, and getting things to production using WebAssembly on the server side of things. So I think that makes it the whole different story, and that shows practically that the adoption is skyrocketing. And this 2024 will be very special for WebAssembly when it comes to adoption, because this year we'll see more and more number of practical use cases, and we'll see the acceleration in the proposal enhancements as well. I also talked about WASIX, which is WASI plus an add-on capability. So if there are companies like Wasmer who are actually building stuff which is being asked by the customers. So I just wanted to point this because of the adoptability. Like people are using, they are getting, like this is the issue, and then there are certain companies and organizations who are building those extensions and building various things around it or as an add-on capabilities to cater those set of use cases. And I see different runtimes doing it. So yeah, 2024 will again be very interesting to see how WebAssembly grows, and definitely it will grow, that's for sure. And that is why we also thought that 2024 will be the best time to get you started in the first month itself, get your gear set and learn about WebAssembly. And now you get on by creating some cool stuff with WebAssembly. So yeah, that's pretty much it from our side, and we hope that you enjoy the course. So if you have learned something from the course, it's free to share. So please share that in your network for anyone who wants to learn about WebAssembly on the server side, cloud native angle, observability, machine learning, and different aspects that Rishit just mentioned. Do let us know if you face any difficulties. Do try out the examples, post in the comments what you are building or what you have learned from this particular course. From the creator's perspective, I really enjoyed building this course with Rishit, cross time zones. It has been really fun building the complete course. It was challenging to identify what all we want to cover, what all we want to skip, what all we don't want to cover, and get the whole a usable course that gives you something out there. So yeah, that's pretty much it. And thank you so much for watching.